Did you know that for every grain of sand on Earth, there are 10,000 stars in the Milky Way? Or that a monstrous black hole lurks at its center, invisible yet powerful enough to shape our galactic home? Join us as we take you on a fascinating journey through the mysteries of our Milky Way galaxy. The Milky Way galaxy is often described as a barred spiral galaxy, characterized by its distinctive swirling arms that extend outwards from a central bulge. This central bulge, where stars are densely packed, contributes to the galaxy's overall shape. The galaxy is approximately 100,000 light-years in diameter, creating a vast expanse of space filled with billions of stars, gas, and dust. While our perspective from Earth makes it challenging to see the Milky Way in its entirety, astronomers have mapped its structure using various techniques, including observations from space telescopes. This has revealed that the Milky Way is not a perfect disk. Rather, it has a slight warp and unevenness due to gravitational interactions with neighboring galaxies and dark matter, which plays a significant role in shaping its structure. In addition to the glowing stars that we see, the Milky Way is surrounded by a more extensive halo of dark matter, which does not emit light, but exerts its gravitational influence on the galaxy. The total mass of the Milky Way, including stars, gas, dust, and dark matter, is estimated to be around 1 trillion times the mass of our Sun. This substantial mass holds the galaxy together, influencing the orbits of stars and other celestial bodies within it. Interestingly, the Milky Way is not alone in the cosmos. It is part of a group known as the Local Group, which includes more than 50 galaxies, with the Andromeda Galaxy being the largest. This group is just one of many collections of galaxies across the universe, highlighting the vastness and complexity of cosmic structures. The Milky Way, with its barred spiral shape and immense size, serves as a beautiful reminder of the intricate architecture of the universe. Estimates suggest there are between 100 billion to 400 billion stars in the Milky Way galaxy. This staggering number highlights the richness and complexity of our cosmic neighborhood. Despite its vastness, our galaxy's stellar population remains relatively poorly understood. Many stars are too faint or distant to observe directly. Astronomers typically rely on various methods to estimate star counts, including examining surveys that detect stars based on their brightness and distance. These observations are often complicated by the presence of interstellar dust, which can obscure certain regions of the galaxy, making it challenging to see every star shining within. The Milky Way is home to many different types of stars, ranging from massive blue giants to small red dwarfs. Interestingly, red dwarfs are the most common type, and they are known to be dim and long-lived, making them difficult to count. In fact, some estimates suggest that most stars in our galaxy may be red dwarfs. Moreover, the Milky Way harbors not just stars, but also a significant number of stellar remnants, such as white dwarfs, neutron stars, and black holes. Each star that has lived and died contributes to the rich tapestry of the galaxy, adding both beauty and complexity to our understanding of its life cycle. At the center of the Milky Way galaxy lies a supermassive black hole known as Sagittarius A star. This black hole is estimated to have a mass of about 4 million times that of our Sun, making it a colossal presence in the heart of our galaxy. The discovery of Sagittarius, a star, and the understanding of its properties have revealed much about the dynamics of the Milky Way. The detection of Sagittarius, a star, was a remarkable achievement in astrophysics. Early evidence emerged in the 1980s when astronomers began to notice unusual motions of stars near the galactic center. These stars showed rapid orbital speeds, suggesting they were influenced by an unseen massive object. The mathematics involved in studying these stellar orbits led to the conclusion that a supermassive black hole must be residing there. Further observations with powerful telescopes, such as the Very Large Array and other radio observatories, continued to refine our understanding of this mysterious entity. In the last decade, advanced techniques involving infrared observations have produced incredibly detailed images of the star clusters orbiting Sagittarius A star, providing more compelling evidence of its existence. In 2018, the Event Horizon Telescope project captured the first ever image of a black hole's shadow, further solidifying our understanding of these enigmatic objects. While that image was of a black hole in another galaxy, It represented a significant step in the field of black hole research, enhancing our knowledge of those like Sagittarius, a star at the core of our own galaxy. The ongoing study of this supermassive black hole offers scientists a window into understanding gravitational forces, galaxy formation, and the evolution of cosmic structures. The Milky Way galaxy is rotating at an impressive speed of about 270 kilometers per second, or roughly 600,000 kilometers per hour at the solar system's location, near the outer edge of the galactic disk. This immense velocity reflects the combined gravitational influences of the galaxy's mass, including stars, gas, dust, and dark matter, all of which help to keep the structure intact while maintaining its spiral shape. The rotation speed varies throughout the galaxy. Areas closer to the center tend to rotate faster, while stars farther out, like our Sun, rotate more slowly around the galactic core. The circular orbit of the solar system around the galactic center takes approximately 250 million years to complete, a period also known as a galactic year. This rotation plays a crucial role in the dynamics and structure of the Milky Way. As the galaxy spins, the centrifugal force from this motion counteracts the gravitational pull of the galaxy's mass, contributing to the stability of its spiral arms. Moreover, the movements of stars and gas clouds within these arms help astronomers gauge the overall mass distribution of the galaxy, including the elusive dark matter halo that envelops it. Understanding the rotation of the Milky Way provides insights into its evolution and the gravitational interactions that shape galaxies. It allows scientists to collect data on how stars and galaxies form and interact over cosmic time. Additionally, the study of galactic rotation contributes to our broader understanding of the universe, revealing the gravitational forces that influence structural formation and the life cycle of galaxies themselves. The Milky Way galaxy can be divided into several distinct regions, each characterized by unique properties that contribute to the galaxy's overall structure and behavior. The primary regions include the galactic bulge, the disk, the halo, and the spiral arms, each fulfilling a specific role in the life of the galaxy. The galactic bulge sits at the center of the Milky Way and is densely packed with stars, particularly older stars. This central region is often characterized by a spherical shape and contains a significant number of red giants and variable stars. It also hosts the supermassive black hole known as Sagittarius A star, which influences the orbits of stars in the bulge. The bulge is thought to have formed early in the galaxy's life cycle and serves as a vital study area for understanding stellar evolution and dynamics. Surrounding the bulge is the disk, where most of the galaxy's younger stars, gas and dust reside. This flat, rotating region is where star formation actively occurs, contributing to the galaxy's bright and colorful appearance. The disk is characterized by its spiral arms, which are sites of ongoing star formation and contain clusters of young, hot stars. These arms create a vibrant contrast with the older, more stable stars found in the bulge. Beyond the disk lies the galactic halo, which is a spherical region surrounding the entire galaxy. The halo contains older stars, globular clusters, and a substantial amount of dark matter, which is believed to account for most of the galaxy's mass. The halo's influence is crucial for understanding the gravitational interactions that shape the Milky Way's structure. Unlike the disk, this region is less dense and features stars that are mainly metal-poor, indicating their formation in an earlier universe. Each of these regions plays an integral role in the Milky Way's evolution, providing a context for studying gravitational forces, star formation processes, and the interactions of various celestial bodies. The diversity of these regions reflects the complexity and dynamism of our galaxy, demonstrating how different environmental conditions can lead to the formation and evolution of stars and structures in the universe. The Milky Way galaxy is estimated to be around 13 billion years old, making it one of the older galaxies in the universe. Scientists assess the age of the Milky Way through various techniques, primarily by studying the oldest stars within it, particularly those found in globular clusters and the galactic bulge. Globular clusters are spherical collections of stars that orbit the galaxy. Many of these clusters are incredibly ancient, with the oldest ones dating back to approximately 13 billion years, close to the time when the universe itself began to form. By determining the age of these ancient stars through a process called stellar evolution, scientists can estimate when these clusters formed and, consequently, infer a lower limit on the age of the Milky Way galaxy. Another method utilizes the chemical composition of stars. As stars evolve, they produce heavier elements through nuclear fusion. The oldest stars in the Milky Way, particularly those that formed early on, tend to have lower levels of heavy elements, indicating they were formed in a primordial environment. By analyzing the abundance of these elements, particularly iron, astronomers can estimate the formation timeline of the galaxy. This approach reveals that the Milky Way began forming just a few 100 million years after the Big Bang. Finally, studies of the galaxy's structure and the distribution of its various components also provide clues. Observations of the gradients in age and composition across the galaxy indicate how and when different regions formed. The continuous monitoring of stellar movements and interactions further refines these age estimates, helping scientists paint a comprehensive picture of the Milky Way's evolutionary history. Understanding the age of the Milky Way not only allows scientists to place our galaxy within the grand timeline of the universe, but also helps illuminate the processes of galaxy formation and the conditions present in the early universe. The fate of the Milky Way galaxy is a fascinating topic that involves both gradual evolution and dramatic events. In about 4 billion years, the Milky Way is expected to collide with its neighboring galaxy, Andromeda. This gravitational encounter will initiate a series of cosmic fireworks as the two galaxies interact, leading to a spectacular merger that will reshape both structures. The stars within these galaxies are so far apart that direct collisions between them are unlikely. However, their gravitational forces will cause significant changes, leading to new star formation in regions where gas and dust are compressed. As time progresses, this merger will ultimately result in a new larger galaxy, sometimes referred to as Milkomeda or Milkdromeda. Following the collision, the remnants of both original galaxies will settle into a more stable configuration. Over several billion years, the newly formed galaxy will continue to evolve, with its stars reorganizing into new orbits within the combined structure. The long-term future also includes the fate of the universe itself. The Milky Way, along with the new galaxy formed from the merger with Andromeda, may eventually find itself part of an increasingly isolated region of the universe as the expansion accelerates due to dark energy. As galaxies drift further apart, interactions with nearby galaxies will diminish. In the very distant future, perhaps tens of billions of years from now, the Milky Way and its merged counterpart may become home to mostly older stars, with fewer new stars being born as the gas available for star formation becomes depleted. Eventually, the remaining stars will fade, leading to a dark and quiet galaxy populated primarily by white dwarfs, neutron stars, and black holes. This slow, gradual decline towards a more inert state represents a far-off but intriguing conclusion to the life of our galaxy. Mapping the Milky Way galaxy from within presents unique challenges due to our position inside its disk. However, astronomers employ various techniques and tools to chart its structure and comprehend its dynamics. One effective approach involves observing different wavelengths of light, including radio, infrared, and optical waves, which provide complementary information about different components of the galaxy. Radio observations are particularly valuable because they can penetrate the dense clouds of dust that obscure parts of the galaxy, allowing astronomers to map the distribution of neutral hydrogen gas, which is abundant throughout the Milky Way. By examining the wavelengths emitted by this gas, scientists can create detailed maps of the galaxy's spiral arms and identify areas of star formation. Additionally, large survey projects such as the HI survey and the Sloan Digital Sky Survey utilize radio telescopes and ground-based instruments to produce comprehensive maps of the galaxy's structure. Infrared observations are another critical technique, as they can penetrate dust more effectively than visible light. Space telescopes like the Spitzer Space Telescope and the Wide Field Infrared Survey Explorer have played significant roles in mapping the galaxy. They reveal the locations of young stars and regions of ongoing star formation, providing a clearer picture of the inner workings of the Milky Way. Moreover, the study of stellar populations and their movements helps astronomers derive a three-dimensional map of the galaxy. By tracking the positions and velocities of stars, especially those in the galactic bulge and disk, scientists gather information about the gravitational influences at play within these regions. The Gaia satellite has expanded our understanding of the Milky Way by providing highly precise measurements of the positions, distances, and motions of billions of stars, contributing to the creation of an unprecedented, detailed map of our galaxy. Together, these methods allow astronomers to piece together the structure and dynamics of the Milky Way, enriching our understanding of its formation, evolution, and the vast cosmic environment in which it exists. The ongoing advancements in observational technology continue to refine these maps, revealing a galaxy that is complex and dynamic, with new discoveries waiting to unfold. The Milky Way galaxy is filled with unique features that set it apart from other galaxies in the universe. One of the most remarkable characteristics is its spiral structure, known as a barred spiral galaxy, which features prominent spiral arms extending outwards from a central bar-shaped formation of stars. These spiral arms are bustling with star formation, containing a significant amount of gas and dust, making them vibrant hubs of activity. This structure is not only visually striking but also plays a crucial role in the processes of starbirth and the evolution of the galaxy. Another unique feature is the presence of the supermassive black hole located at the center of the galaxy called Sagittarius A star. This black hole has a mass that is roughly 4 million times that of our Sun. Its gravitational influence governs the orbits of the stars in the core, allowing astronomers to study its properties and the dynamics of the surrounding stars. The detection and study of Sagittarius A star have provided profound insights into the behavior of black holes and their roles in galaxy formation. Additionally, the Milky Way is home to diverse stellar populations. It contains a mix of older stars, found predominantly in its bulge and halo, and younger stars in the disk, especially within the active star-forming regions of the spiral arms. This stellar diversity is further highlighted by the presence of globular clusters, which are tightly packed groups of ancient stars orbiting the galaxy. These clusters provide a glimpse into the early history of the Milky Way and the conditions that prevailed shortly after its formation. The Milky Way's interaction with neighboring galaxies also adds to its uniqueness. It is part of the Local Group, which includes the Andromeda Galaxy and several smaller galaxies. The gravitational interactions with these nearby galaxies create fascinating dynamics, such as tidal forces that reshape their structures and will eventually lead to the anticipated collision with Andromeda in the future. This ongoing interaction highlights the Milky Way as an active participant in the cosmological tapestry, evolving alongside its celestial neighbors over vast timescales. The Milky Way galaxy is one of the countless galaxies that fill the universe, and while it has its unique characteristics, it also shares several features with other galaxies. One of the most significant distinctions is its classification as a barred spiral galaxy. This classification is similar to several other well-known galaxies, including the Andromeda Galaxy. However, the Milky Way is distinguished by the presence of a central bar, a feature that helps facilitate the movement of stars and gas within the galaxy. In terms of size, the Milky Way is medium to large compared to other galaxies. It spans approximately 100,000 light-years in diameter and contains roughly 100 billion to 400 billion stars. Some galaxies, like the giant elliptical galaxy IC 146, can be several times larger than the Milky Way, while smaller dwarf galaxies have far fewer stars and less mass. The Milky Way is relatively average in that it belongs to the Local Group, a collection of more than 50 galaxies, highlighting the diversity present in the universe. Another interesting aspect is the Milky Way's dark matter halo, which extends significantly beyond its visible components. This halo is consistent with findings in other galaxies, where dark matter plays a critical role in governing the rotation and structure of galaxies. Most galaxies are thought to contain large amounts of dark matter, which does not emit light and can only be detected through its gravitational effects. This dark matter is pivotal in understanding cosmic evolution and the formation of galaxies throughout the universe. The Milky Way also has a history of interaction with nearby galaxies. It has experienced gravitational influences from smaller companions, such as the Large and Small Magellanic Clouds. Many galaxies in the universe have similarly interacted with others, leading to mergers, collisions, and the exchange of stars and gas. These interactions shape the evolution of galaxies, including their star formation rates and overall structure. While the Milky Way stands as a distinctive entity in the cosmic landscape, it shares the fundamental processes of formation and evolution that characterize galaxies throughout the universe, making it a vital part of the broader tapestry of cosmic history. Stars are born in the Milky Way through a complex process that primarily occurs in vast regions of gas and dust, known as molecular clouds. These clouds are often referred to as stellar nurseries due to the dense, cold conditions that facilitate star formation. Within these clouds, gravitational forces can cause regions to collapse under their own weight, leading to the formation of dense cores. As these cores become denser, the temperature and pressure within them rise. When the core reaches a critical density, hydrogen gas begins to fuse into helium through nuclear fusion. This process releases an immense amount of energy, and the emerging heat counteracts the gravitational collapse, allowing the core to stabilize into what is known as a protostar. During this phase, the protostar continues to accumulate mass from the surrounding material, growing larger and hotter. As the protostar evolves, it further compresses the material around it, eventually clearing out its immediate vicinity. Once the temperature within the core rises sufficiently high to sustain nuclear fusion, the protostar ignites to become a main sequence star, which represents the primary energy-producing phase of a star's life. This ignition marks the moment when the star begins to shine brightly, and it enters a stable period where it will spend the majority of its life. Interestingly, the conditions in molecular clouds are conducive not just to the formation of individual stars, but to the birth of groups or clusters of stars. In regions of dense gas, multiple stars can form at once, sometimes leading to the creation of star clusters. These clusters typically contain dozens to thousands of stars that share a similar age and chemical composition. As stars continue to form, they interact with each other gravitationally, influencing their trajectories and fates over time. This dynamic process of star birth, coupled with the interactions among new stars, plays a vital role in shaping the Milky Way galaxy and contributes to our understanding of stellar evolution. The Milky Way is home to a diverse variety of stars, each exhibiting distinct characteristics and evolutionary stages. One of the most common types of stars are red dwarfs, which are small and relatively cool. These stars make up the majority of the stellar population in the galaxy, distinguished by their long lifespans, often lasting trillions of years. Their low brightness and small size make them difficult to detect without advanced observational techniques. Another significant category includes main sequence stars, which are in a stable phase of hydrogen fusion in their cores. Our Sun is a prime example of a G-type main sequence star, characterized by a medium size and temperature. The main sequence classification includes a spectrum of stellar types, ranging from more massive and hotter O-type stars to cooler, smaller M-type stars. The lifespans and evolutionary paths of these stars differ significantly, with massive stars burning through their fuel much more quickly than their smaller counterparts. Beyond the main sequence, there are giants and supergiants. Red giants are evolved stars that have used up the hydrogen in their cores and have begun to expand and cool. They can be several times larger than the Sun and exhibit much greater luminosity. Supergiants, such as Betelgeuse or Antares, are even larger and more luminous, representing some of the most massive stars in the galaxy. These stars have short lifespans, often concluding their lives in spectacular supernova explosions. Additionally, the Milky Way hosts a variety of stellar remnants which play a crucial role in its overall composition. White dwarfs are the remnants of small to medium-sized stars that have exhausted their nuclear fuel and shed their outer layers. Neutron stars, formed from the remnants of powerful supernova explosions, are incredibly dense and composed mainly of neutrons. Finally, black holes, which can form from the collapse of massive stars, represent some of the most enigmatic objects in the galaxy. Each type of star contributes to the rich tapestry of the Milky Way, influencing the dynamics, evolution, and chemical composition of our galaxy. Massive stars, those with at least 8 times the mass of our Sun, undergo a spectacular and often violent end to their life cycles. Once they exhaust the hydrogen fuel in their cores, these stars enter a series of nuclear fusion stages, where they fuse heavier elements such as helium into carbon, and subsequently carbon into heavier elements like oxygen and silicon. This process continues until the core is primarily composed of iron, which cannot release energy through fusion. At this critical point, the balance between the inward pull of gravity and the outward pressure generated by nuclear fusion shifts dramatically. Unable to sustain fusion reactions, The core collapses under its own gravity, leading to a catastrophic explosion known as a supernova. This explosive event is incredibly energetic, often outshining entire galaxies for a brief period and releasing an immense amount of energy and material into space. The impact of supernovae on the galaxy is profound. These explosions not only disperse heavy elements, which originated from the fusion processes in the star's core, but also inject these elements into the interstellar medium. This enriches the surrounding gas and dust, providing the building blocks for future star and planet formation. Elements such as carbon, oxygen, and iron, crucial for the development of life as we know it, are formed during these stellar processes and shared with the galaxy upon the star's death. Additionally, supernovae can trigger the collapse of nearby molecular clouds, leading to new cycles of star formation. The shock waves generated by the explosion compress surrounding gas, facilitating the birth of new stars. The violent death of massive stars acts as a critical driver for the evolutionary processes within the galaxy, influencing stellar populations and contributing to the overall chemical enrichment of the Milky Way. Furthermore, the remnants of massive stars can become neutron stars or black holes, which hold significant gravitational influences that affect nearby stars and gas. Neutron stars, particularly those that are rapidly spinning, can emit beams of radiation as pulsars, providing astronomers with valuable insights into the behavior of matter under extreme conditions. Ultimately, the life cycle of massive stars is integral to the ongoing evolution of the Milky Way, revealing the interconnectedness of stellar and galactic dynamics. Neutron stars are incredibly dense remnants of massive stars that have undergone a supernova explosion. They are born when a massive star, typically with a mass between 8 and 20 times that of our Sun, exhausts its nuclear fuel. This exhaustion leads to the collapse of the star's core once nuclear fusion can no longer counteract the immense gravitational pressure. What remains after the outer layers are expelled in a supernova is the core, which contracts into a neutron star. The core's density becomes so extreme that protons and electrons are forced together under such pressure that they combine to form neutrons. This process transforms the core into a dense object made almost entirely of neutrons, resulting in a stellar remnant that is roughly the size of a city, yet containing a mass greater than that of the Sun. 1 teaspoon of neutron star material would weigh about 6 billion tons, making them one of the densest forms of matter in the universe. Neutron stars have several remarkable properties. Due to their rapid rotation, which can be several hundred times per second, they can emit beams of radiation from their magnetic poles. When these beams are aimed at Earth, they are detected as pulsars, characterized by their regular pulsing intervals. This unique rotational speed, combined with their strong magnetic fields, creates an environment that provides invaluable data for astronomers studying the physics of extreme conditions. As remnants of supernovae, neutron stars also play an essential role in the galactic ecosystem. They contribute to the recycling of heavy elements into the interstellar medium, enriching the gas and dust from which new stars and planets can form. Additionally, the existence of neutron stars can also influence nearby stars through their gravitational pull, potentially leading to binary systems where interactions between the two objects can result in various phenomena such as X-ray emissions or gravitational waves. The study of neutron stars continues to shed light on fundamental questions about the nature of matter and the life cycles of stars, deepening our understanding of the complex workings of the universe. Binary star systems, which consist of 2 stars orbiting a common center of mass, can arise from several formation processes. The most common theory suggests that they emerge from the same molecular cloud. As these clouds collapse under their own gravity, they can fragment, creating multiple dense regions. These developing protostars can then gravitationally attract each other, leading to the formation of a binary system. The evolution of binary stars is intricately tied to their orbital dynamics and the characteristics of each star. Initially, they might evolve similarly if they are of comparable size and mass. As they age, various factors can influence their paths. For example, they may exchange mass through a process called mass transfer, where one star can pull material from its companion, significantly altering their life cycles. In some instances, a binary star system can have one star that evolves much more quickly than the other. This typically happens in cases where there is a large disparity in their sizes. The more massive star will exhaust its nuclear fuel first, potentially becoming a red giant, and later transition into a supernova, leaving behind a neutron star or black hole. Meanwhile, the less massive companion will continue its own life cycle, possibly even evolving into a red giant itself long after the other has exploded. Additionally, binaries have a fascinating role in stellar population studies. Observing pairs of stars allows astronomers to determine their masses and ages through gravitational interactions. This provides critical insights into stellar evolution, as well as the characteristics of the galaxies they inhabit. The interplay between the two stars can also result in various exotic phenomena, such as the creation of cataclysmic variables or even gravitational wave emissions when compact objects like black holes or neutron stars collide. Brown dwarfs are intriguing celestial objects that occupy a unique space between the largest gas giants and the smallest stars. Typically, they form in much the same way as stars, from collapsing gas clouds. However, they lack sufficient mass to ignite the nuclear fusion of hydrogen in their cores, which is the defining process that categorizes stars. Instead, their masses usually range from about 13 to 80 times that of Jupiter. And while they may initiate some fusion of deuterium, a heavier isotope of hydrogen, this reaction is short-lived. The significance of brown dwarfs lies in their ability to bridge the gap between stars and planets. These objects provide essential insights into the formation and evolution of both stellar and planetary systems. Understanding brown dwarfs helps scientists to comprehend the processes that govern the birth of stars and the dynamics within star-forming regions. They are also key to studying the low-mass limit of stellar formation and exploring the extremes of gravitational collapse. Another compelling aspect of brown dwarfs is their role in the search for exoplanets. A significant number of brown dwarfs are found in the vicinity of stars, creating an opportunity for astronomers to investigate the interactions between these different types of celestial bodies. Their characteristics can reveal valuable information about the environment in which planets form, as many exoplanets have been discovered in systems that include brown dwarfs, enhancing our understanding of diverse planetary systems. Additionally, brown dwarfs exhibit fascinating atmospheric properties. Some have been shown to have weather patterns and complex chemical compositions akin to those found on Jupiter and Saturn. By studying these objects, researchers can learn more about the atmospheric processes that govern planetary atmospheres, thereby expanding our knowledge of both our solar system and those beyond. This exploration furthers our understanding of where and how life might exist in the universe. Stars are the cosmic foundries where the vast majority of elements found in the universe are produced through the process of nuclear fusion. At the core of a star, extreme temperatures and pressures create the perfect environment for atomic nuclei to collide and fuse together. This process begins with the fusion of hydrogen atoms, which is the most abundant element in the universe. When hydrogen nuclei combine, they form helium and release a substantial amount of energy in the form of light and heat, illuminating the star and allowing it to shine. As stars evolve, their cores become increasingly hot and dense, enabling them to fuse heavier elements. In more massive stars, after hydrogen is exhausted, helium fusion begins, resulting in carbon and oxygen. As these stars continue to evolve and reach higher temperatures, they can undergo further fusion cycles, creating progressively heavier elements such as neon, magnesium, and iron. Each stage of fusion releases energy, sustaining the star and counteracting gravitational collapse. The process does not stop there. When massive stars, those with more than 8 times the mass of our Sun, exhaust their nuclear fuel, they undergo a cataclysmic event known as a supernova. This explosive death yields incredible temperatures and pressures, providing the necessary conditions for the creation of even heavier elements, such as gold, silver, and uranium, through rapid neutron capture processes. The shock waves from the supernova eject these newly formed elements into space, enriching the surrounding interstellar medium with the essential building blocks for future stars and planets. Smaller stars, like our Sun, end their lives more gently as red giants. While they primarily contribute to the dispersal of lighter elements like carbon and oxygen, the material they cast off also becomes part of the next generation of stars and planets. This continuous cycle of stellar birth and death, known as the cosmic cycle of matter, ensures that the universe is constantly replenished with a diverse array of elements, ultimately supporting the formation of planets, life, and all the complexities found within the cosmos. The life cycle of a Sun-like star begins in a molecular cloud, a dense region of gas and dust in space. Under the influence of gravity, portions of this cloud collapse to form clumps that eventually develop into protostars. During this phase, the core of the protostar accumulates mass and heats up, while the surrounding material continues to fall inward, driven by gravity. When the temperature and pressure in its core become high enough, nuclear fusion begins, converting hydrogen into helium. This marks the star's entry into the main sequence phase, where it will spend the majority of its life, roughly 10 billion years for a star of solar mass. As the hydrogen fuel in the core is gradually consumed, the core contracts and heats up, while the outer layers start to expand. This signals the star's transition into the red giant phase. During this period, helium accumulates in the core, and once the temperature is sufficient, helium fusion begins to create carbon and oxygen. The outer layers of the star continue to expand significantly, and it may lose mass through powerful solar winds, reshaping its outer envelope. Eventually, when a Sun-like star runs out of helium, it undergoes additional changes. It cannot sustain further fusion beyond carbon and oxygen in the core, leading to its ultimate decline. The outer layers are expelled into space, forming a beautiful shell of gas and dust known as a planetary nebula. This process not only contributes to the recycling of material in the galaxy, but also leaves behind the core of the star. What remains is a white dwarf, a hot and dense remnant composed mostly of carbon and oxygen. Over billions of years, this white dwarf cools and fades, eventually becoming a cold, dark stellar object. The entirety of this life cycle illustrates not only the remarkable transformations a Sun-like star undergoes, but also its significant role in enriching the universe with elements that will contribute to new stars and planetary systems. This cyclical pattern highlights the ongoing transformation and evolution of stellar matter throughout the cosmos. Globular clusters are densely packed groups of stars that orbit galaxies and are typically among the oldest stellar populations in the universe. Their formation is believed to occur early in a galaxy's history, likely during the intense periods of star formation that characterized the early universe. The prevailing theory suggests that these clusters form from large gas clouds that collapse under their own gravity, leading to a rapid burst of star formation. Many stars are born in a relatively short time frame, resulting in the tightly bound spherical structures that we observe today. As globular clusters evolve, their stellar populations experience various processes that affect their dynamics and characteristics. Initially, the majority of the stars in a globular cluster are of similar age and composition because they formed from the same molecular cloud. However, as time progresses, the stars will continue to evolve. More massive stars will exhaust their nuclear fuel first, eventually becoming red giants and subsequently ending their lives as supernovae, neutron stars, or black holes. These processes can dramatically alter the mass distribution in the cluster and even lead to the formation of stellar remnants at its center. Another significant aspect of globular cluster evolution is the phenomenon of dynamical interactions among stars. Because they are so densely packed, gravitational interactions can lead to encounters where stars exchange energy and momentum. Over time, this causes some stars to be ejected from the cluster, while others sink towards the center, creating a denser core region. This process, known as cluster evaporation, helps to shape the structure of the cluster over billions of years. The evolution of globular clusters is also influenced by their interactions with the host galaxy. As they orbit their galaxy, they can experience tidal forces that can stretch or distort their shapes. These clusters primarily reside in spherical halos surrounding galaxies, and their interactions with gas and dark matter in the galaxy can lead to further dynamical changes. Eventually, the cumulative effects of stellar evolution, dynamical interactions, and galactic influences contribute to the unique characteristics of globular clusters that we observe today, allowing astronomers to study them for insights into the formation and evolution of galaxies themselves. The oldest stars in the Milky Way are known as Population 2 stars, with some of the most ancient examples found in globular clusters. These stars, which are typically over 12 billion years old, formed during the early phases of the universe, shortly after the Big Bang. One of the most celebrated among these is a star named BD plus 17 degrees 3248, often cited as the oldest known star. Its age is estimated to exceed 13 billion years, giving astronomers a direct glimpse into the conditions of the early universe. Studying these ancient stars provides invaluable insights into the chemical composition of the early Milky Way and the nature of the universe at that time. Since these stars formed when the cosmos was predominantly composed of hydrogen and helium, they are thought to have very low metallicity, meaning they contain minimal amounts of heavier elements. This characteristic allows researchers to infer details about the processes that led to the production of elements in the universe, including how the first stars and supernovae contributed to the chemical enrichment of the surrounding interstellar material. Moreover, ancient stars serve as important cosmic chronometers, helping scientists unravel the history of star formation and the evolution of the galaxy. By determining their ages and comparing them with the ages of globular clusters, astronomers can piece together a timeline of events that shaped the early Milky Way. This also sheds light on the early cosmic environment, including the birth and death of stars, as well as the formation of galaxies during that epoch. In addition to their role in understanding the past, these old stars can offer clues about the formation of stellar systems and the potential for life elsewhere in the universe. Their long-lived nature means they have endured the passage of time, providing a window into the processes that govern stellar evolution. This makes them not only fascinating objects of study, but also vital components in the larger narrative of cosmic history, illuminating the pathways leading toward the complex structures we observe today. Planetary systems are quite common throughout the Milky Way galaxy, with recent discoveries indicating that most stars have at least one planet. Estimates suggest that there are hundreds of billions of stars in our galaxy, and various studies propose that more than half of these stars host planets, resulting in potentially hundreds of billions of planets in total. Many of these planetary systems can exhibit a diverse range of configurations, from single planets orbiting close to their stars to multiple planets in complex arrangements. The advent of space telescopes, particularly the Kepler Space Telescope, has transformed our understanding of planetary systems. Kepler discovered thousands of exoplanets, and its data revealed that planets vary widely in size, composition, and orbital characteristics. Furthermore, many stars are found to possess multiple planets, leading to the notion that systems like our own solar system are likely more common than previously thought. The distribution of planets is not uniform. Different types of stars show different probabilities of hosting planetary systems. For instance, red dwarfs, which are the most abundant type of star in the Milky Way, have been found to have a higher prevalence of planets compared to more massive stars. Factors such as the star's mass, age, and environment contribute to the likelihood of planet formation. Moreover, current research is delving deeper into the characteristics of these planets. Scientists are particularly interested in the so-called habitable zone, where conditions might support liquid water, an essential ingredient for life as we know it. As more planetary systems are studied, astronomers are hopeful that they will uncover a multitude of new worlds, some of which may bear similarities to Earth. This ongoing investigation into planetary systems expands our understanding of the universe and raises fascinating questions about the potential for diverse forms of life beyond our own planet. The discovery of exoplanets has unveiled a stunning variety of planetary types, each revealing the incredible diversity found in our galaxy. Among the most commonly identified categories are gas giants, similar to Jupiter and Saturn in our solar system. These massive planets primarily consist of hydrogen and helium, often encircled by extensive systems of rings and moons. Some gas giants have been found in close orbits around their stars, leading to the classification of hot Jupiters. These planets experience extreme temperatures due to their proximity to their star, creating conditions markedly different from those observed in our own solar system. In addition to gas giants, a significant number of smaller rocky planets, known as terrestrial exoplanets, have been identified. These planets are composed of solid surfaces similar to Earth and Mars. Many of the terrestrial exoplanets discovered are found within the habitable zones of their stars, where temperatures might allow for liquid water. Some of these rocky planets are even categorized as Earth-like, leading to increased interest in their potential to host life. Beyond these categories, scientists have also identified a group of planets called super-Earths. These worlds are larger than Earth, but smaller than gas giants, typically ranging from 1 to 10 times the mass of our planet. Super-Earths can possess a diverse range of characteristics, potentially featuring solid surfaces, thick atmospheres, or even oceans. The discovery of such planets has broadened our understanding of planetary formation and the conditions necessary for life. Another intriguing category includes mini-Neptunes, which are smaller versions of Neptune and can have thick atmospheres of hydrogen and helium. These planets often lie between the super-Earths and gas giants in terms of mass and size, raising questions about their formation processes and atmospheric dynamics. The ongoing exploration of exoplanets continues to reveal new discoveries, each of which enhances our comprehension of not only planetary systems within the Milky Way, but also the potential for alternative forms of life in the universe. Scientists employ a variety of methods to detect and study exoplanets, each leveraging different principles of astronomy and physics. One of the most effective techniques is called the transit method. This approach involves monitoring the brightness of a star over time. When a planet passes in front of its host star, it causes a temporary decrease in brightness, or transit. By measuring the amount of light blocked and the duration of the transit, astronomers can infer the size of the planet and its distance from the star. Another prominent technique is the radial velocity method, which focuses on the gravitational effect that planets exert on their stars. As a planet orbits, its gravitational pull causes the star to wobble slightly. This motion affects the star's light spectrum, leading to observable shifts towards the red or blue end of the spectrum, known as the Doppler effect. By analyzing these shifts, scientists can determine the mass of the planet and its orbital characteristics, providing insights into the planet's composition and potential habitability. Direct imaging is also an important technique, although it is more challenging. In this method, astronomers use advanced instruments to capture images of planets directly. This is often done by blocking out the light from the star, allowing the fainter light from the planet to be detected. While this method has been successful for some giant exoplanets, it remains difficult due to the overwhelming brightness of stars. Once exoplanets are detected, scientists continue their study using spectroscopic analysis. By examining the light that filters through an exoplanet's atmosphere during a transit, researchers can identify elements and compounds present, such as water vapor, carbon dioxide, and potential biosignatures. The analysis of these atmospheric compositions can provide critical information about the conditions on these distant worlds, including their potential to support life. The combination of these methods enables a comprehensive understanding of exoplanets, fostering a deeper appreciation for the diverse array of planetary systems within our galaxy. The habitable zone, often referred to as the Goldilocks zone, is the region around a star where conditions are just right for liquid water to exist on the surface of a planet. This concept is fundamental in the search for extraterrestrial life because liquid water is considered a key ingredient for life as we know it. The boundaries of the habitable zone depend on the star's luminosity, temperature, and size, which all influence the amount of heat and light reaching orbiting planets. Around stars similar to our Sun, the habitable zone typically lies at a distance of about 1 astronomical unit, the average distance from the Earth to the Sun. However, this zone varies significantly for different types of stars. For example, red dwarfs, which are cooler and less luminous than the Sun, have habitable zones that are much closer to the star, often within a range of a few tenths of an astronomical unit. Conversely, for more massive and hotter stars, the habitable zone is farther out, as these stars produce more energy and heat. The width of the habitable zone can also vary. In the case of cooler stars, the habitable zone may extend further out because planets in these regions can still maintain surface temperatures conducive to liquid water, despite the star itself emitting less energy. For hot stars, the habitable zone may be narrower, and planets need to be positioned precisely to avoid extreme conditions that would make it too hot for water to remain liquid. Environmental factors also play a crucial role in determining whether a planet within the habitable zone can sustain life. For instance, the planet's atmosphere, surface pressure, and geological activity can all significantly affect its climate and the presence of liquid water. As astronomers continue to identify exoplanets within various habitable zones around different stars, the concept of habitability is evolving, emphasizing the complexities of planetary environments and the potential for life in myriad forms throughout the universe. Yes, several Earth-like planets have been discovered in the Milky Way, particularly those located within the habitable zones of their respective stars. These planets, often termed potentially habitable or Earth analogues, exhibit characteristics similar to those of Earth, including size, composition, and distance from their host stars. This similarity raises intriguing questions about their potential to support liquid water and, by extension, life. One of the most notable examples is Kepler 186f, discovered by the Kepler Space Telescope. Kepler 186f orbits a star that is a red dwarf located about 510 light-years away from Earth. This planet is approximately 1.1 times the size of Earth and lies within the star's habitable zone, making it a prime candidate for further study regarding its potential habitability. Another promising find is Proxima Centauri b, which orbits Proxima Centauri, the closest known star to the Sun. Although it is similar in size to Earth and located within its star's habitable zone, its proximity to a red dwarf star means it could face challenges such as stellar flares and radiation, which may affect its atmospheric conditions. Additionally, TRAPPIST-1 is a remarkable system with 7 Earth-sized planets, 3 of which are located within the star's habitable zone. These planets, revolving around an ultra-cool red dwarf star, present exciting opportunities for understanding diverse planetary environments and the factors that influence habitability. The search for Earth-like planets is ongoing, and as new telescopes and technologies come online, astronomers hope to identify even more candidates. The study of these planets not only helps assess their potential for life, but also enhances our understanding of planetary formation and the dynamics of planetary systems throughout the galaxy. Each discovery adds a piece to the puzzle of what makes a world potentially habitable and provides a context for recognizing our own planet in the vast cosmic tapestry. Gas giant planets form through a process that begins with the formation of a protoplanetary disk around a young star. This disk, composed of gas and dust, allows solid materials to coalesce and form the cores of planets. In the case of gas giants, this formation typically occurs when a substantial solid core reaches a critical mass, often estimated to be around 10 times the mass of Earth. Once this threshold is achieved, the core can attract surrounding gas from the disk through its strong gravitational pull, leading to rapid accumulation of hydrogen and helium, creating a massive gaseous envelope. The location of gas giant formation can significantly impact their subsequent evolution. Many gas giants form beyond the frost line, where temperatures are low enough for volatile compounds like water and methane to condense and contribute to the planet's mass. Beyond this line, the gas giant can more easily gather and retain materials, allowing for the development of a substantial atmosphere. The initial conditions of the protoplanetary disk, along with its density and temperature gradients, play crucial roles in determining the exact location of gas giant formation. Migration is another critical aspect of gas giant development within planetary systems. Once formed, gas giants can undergo a process known as planetary migration, where their orbits change due to gravitational interactions with the protoplanetary disk or other planets. One common scenario is called Type 1 migration, where a gas giant interacts with the gas in the disk, causing it to move inward or outward based on the torque exerted by the material. This process could lead gas giants to settle closer to the star or to wander into different orbital configurations. Type 2 migration occurs when the planet clears a gap in the protoplanetary disk due to its size and mass. In this case, the planet moves steadily through the disk material, causing its orbit to shift. Depending on the surrounding environment, gas giants can end up in various configurations, leading to systems with hot Jupiters, gas giants located very close to their stars, or those with more traditional layouts, such as those seen in our own solar system. These migrations are critical not only in determining the arrangement of planets, but also in understanding the diversity of planetary systems observed throughout the Milky Way. Hot Jupiters are a class of exoplanets that are similar in size and composition to Jupiter, but orbit much closer to their parent stars, resulting in significantly higher temperatures. Typically, these gas giants have orbital periods of just a few days or weeks, and can be found within a distance of 1/10 of an astronomical unit from their stars, where conditions can reach extreme levels. Their proximity to their stars leads to intense heating, with surface temperatures often exceeding 1,000 degrees Celsius, creating environments that are vastly different from those of gas giants in our own solar system. The existence of hot Jupiters comes as a surprise to astronomers for several reasons. Initially, most models of planetary formation suggested that gas giants would form in cooler regions beyond the frost line, where temperatures would allow for the accumulation of volatiles like water and gas. Seeing such massive planets located so close to their stars was unexpected, leading to questions about how they could have formed in the first place. Theories proposed that they might have formed in the outer regions of the solar system and then migrated inward, but the mechanisms driving such dramatic shifts in their orbits were unclear. Moreover, the discovery of hot Jupiters challenges previous assumptions about the dynamics within planetary systems. The extreme conditions faced by these planets raise questions about their atmospheres and potential weather patterns. For instance, the intense radiation and heat can lead to substantial atmospheric loss over time, affecting their chemical composition and stability. This variability raises important questions about the fate of gas giant atmospheres when subjected to such extreme stellar environments. The presence of hot Jupiters has transformed our understanding of planetary formation and migration, prompting the development of new theories. These discoveries demonstrate that the diversity of planetary systems is far more complex than previously believed, contributing to the ongoing investigation into the nature of exoplanets and the factors that shape their evolution. As astronomers continue to study hot Jupiters and their interactions within their solar systems, they gain essential insights into the broader processes of planetary formation and the characteristics of worlds beyond our own. Planetary rings are fascinating structures that can form around some planets through various processes. One primary mechanism involves the accumulation of material in a planet's vicinity, which can occur when a moon or comet gets too close to a planet and is torn apart by tidal forces. This phenomenon, known as tidal disruption, occurs when the gravitational pull of the planet exceeds the cohesive forces holding the moon or comet together. The resulting debris creates a ring system around the planet. Another way rings can form is through collisional events. When moons collide with other celestial objects, such as asteroids or comets, the debris generated by these impacts can spread out and form a ring. Similar collisions among existing ring particles can lead to further fragmentation, adding to the material within the ring system. Over time, this process can create rings composed of various sized particles, ranging from tiny dust grains to larger chunks of ice and rock. Moreover, the gravitational influence of moons can play a critical role in maintaining ring systems. Some moons, known as shepherd moons, exert gravitational forces that help confine ring material to specific regions. They can prevent the ring particles from spreading out or being pulled into the planet, effectively shaping the ring's structure. These interactions can result in the formation of gaps and wave patterns within the rings, making them visually striking. Environmental factors can also affect the longevity and evolution of planetary rings. For instance, rings can be influenced by the planet's magnetic field, solar radiation, and the presence of other celestial bodies. Over time, interactions between ring particles and these external forces can lead to changes in the structure and dynamics of the ring system. As astronomical research continues, studying the formation and characteristics of planetary rings helps scientists gain valuable insights into the processes that shape planetary systems, enhancing our overall understanding of the diversity of celestial bodies in the universe. Rogue planets are fascinating celestial bodies that have drifted away from their parent stars and now wander freely through the galaxy without being gravitationally bound to any star system. These planets can form in a variety of environments but are often thought to have originated within protoplanetary disks before being ejected due to gravitational interactions, such as collisions with other planets or close encounters with stars. Additionally, some rogue planets may have formed independently in isolation, accumulating mass from the surrounding gas and dust in their early formation stages. Estimates suggest that rogue planets could be quite common in the Milky Way, potentially outnumbering the stars in the galaxy. Several studies indicate that there could be billions of these unbound worlds. The process of planet ejection can happen more frequently than previously believed, especially in crowded regions of space where gravitational interactions are prevalent, such as in young star clusters or systems with 3 or more interacting bodies. This dynamic environment can lead to significant orbital changes, resulting in the ejection of a celestial body from its original orbit. The study of rogue planets is intriguing for scientists, as it broadens our understanding of planetary systems and the formation processes at play in the universe. Unlike planets that remain tied to their stars, rogue planets can potentially harbor unique atmospheres and geological characteristics shaped by their varied histories. Observations of these wandering worlds raise questions about their potential to support life and their role in the distribution of materials and elements across the galaxy. Recent advancements in observational techniques may eventually enable astronomers to detect rogue planets more directly. The challenges of identifying these planets arise from their dimness and distance from any nearby star. However, as technology improves and new surveys are undertaken, scientists hope to uncover more about these elusive objects and what they can tell us about the formation and evolution of planetary systems throughout the cosmos. Planetary moons can form through several mechanisms, each contributing to the diverse moon systems observed around different planets. One primary method is through the process of accretion, where dust and gas in a primordial disk surrounding a young planet come together to form a solid body. This is similar to the way planets themselves grow in size. As these materials collide and stick together, they can create larger bodies, eventually forming moons. Another way moons can originate is through what we refer to as capture. This occurs when a passing object, often an asteroid or a comet, comes close enough to a planet's gravitational pull and is drawn in, becoming a moon. This method is responsible for many of the irregular moons seen orbiting larger planets, like those found around Jupiter and Saturn. Additionally, some moons may have been born from the debris resulting from giant impacts, where a large object collides with a planet, ejecting material that can coalesce into a moon over time. The role of moons within their planetary systems is multifaceted. They can influence a planet's tides due to their gravitational pull, creating fluctuations in liquid bodies. This can significantly impact the planet's climate and atmosphere. Moons also provide insight into planetary formation and dynamics. For instance, Studying a moon's surface and composition can reveal much about the history of its parent planet and the conditions in the early solar system. Moreover, moons are essential for understanding the potential for life elsewhere. For example, some moons like Europa and Enceladus possess subsurface oceans beneath their icy crusts, raising questions about the possibility of life beyond Earth. By examining these moons, scientists hope to gather clues about life's potential in the universe. Each moon signifies a unique story about its planet and contributes to the rich tapestry of our cosmic neighborhood. The spiral arms of the Milky Way are one of the most distinctive features of our galaxy, resembling large, flowing tendrils of stars, gas, and dust that extend outward from the galactic center. There are several main arms and some smaller ones, all of which are rich in young hot stars. The Milky Way itself is classified as a barred spiral galaxy, meaning it has a central bar shape that influences the structure of its arms. The formation of these spiral arms is primarily attributed to a phenomenon known as density waves. As stars and gas in the galaxy move in orbits around the center, they do not all travel at the same speed due to gravitational interactions and other forces. This differential motion creates areas of higher density, which leads to the clustering of stars and gas. These regions become the spiral arms we observe today, characterized by a higher concentration of materials compared to the space between them. The arms are not static. They are dynamic structures that continuously form and dissipate over millions of years. New stars are born within these arms from the gas and dust that accumulate there, while older stars can drift into the inter-arm regions, making the arms themselves ever-changing. This ongoing cycle of star formation and movement contributes to the vibrant and diverse ecosystems of stars found throughout the galaxy. Interestingly, the Milky Way's spiral arms can also affect the development of planetary systems. As the density waves pass through the interstellar medium, they trigger the collapse of gas clouds, leading to new star formation. This process can enhance the likelihood of planets forming around these new stars. Thus, the spiral arms play a crucial role in the continual evolution of the galaxy, highlighting the complex interactions that shape our cosmic environment. Dark matter is a mysterious and invisible substance that makes up approximately 27% of the universe's total mass and energy. Unlike ordinary matter, which forms stars, planets, and living organisms, dark matter does not emit, absorb, or reflect light, making it undetectable by conventional telescopes. Its presence is inferred from gravitational effects on visible matter and radiation, particularly in the movements of galaxies and galaxy clusters. In the Milky Way and other galaxies, dark matter plays a vital role in shaping the galactic structure. Observations show that stars at the outer edges of galaxies orbit much faster than would be expected based solely on the visible matter present. This discrepancy suggests that there is more mass-exerting gravitational influence than what we can see. Dark matter provides this additional gravitational pull, helping to keep stars in their orbits and maintaining the stability of the galaxy. The distribution of dark matter seems to form a halo around galaxies. This halo extends far beyond the visible structure, creating a larger gravitational field that affects the motion of galaxies and galaxy clusters. It also appears to influence the formation of large-scale structures in the universe. Dark matter's gravitational effects encourage the clustering of galaxies into filaments and sheets, creating the intricate web-like structure observed in universe maps. Understanding dark matter is crucial for comprehending the overall evolution of the universe. Its influence on the Milky Way structure directly impacts star formation and the dynamics of the galaxy, linking it to cosmic phenomena on an enormous scale. While the exact nature of dark matter remains one of the greatest mysteries in contemporary astrophysics, ongoing research continues to explore its properties and the role it plays in the universe's grand design. The galactic halo is a vast, roughly spherical region that surrounds the main body of the Milky Way galaxy. This halo contains a mix of dark matter, older stars, globular clusters and a sparse amount of gas. Extending far beyond the visible components of the galaxy, the halo plays a crucial role in shaping our understanding of the Milky Way's mass distribution and the gravitational dynamics at play within it. The stars in the galactic halo are typically older and less chemically enriched than those found in the galactic disk, where new stars form from gas and dust. This difference can provide valuable clues about the early history of the Milky Way. The existence of these ancient stars suggests that the halo formed early in the galaxy's life, likely during the initial phases of its accumulation and growth. The presence of globular clusters, which are densely packed groups of older stars, further indicates the halo's antiquity, as these clusters are thought to be remnants of the galaxy's formation processes. Studying the distribution and motion of objects within the halo can help scientists understand the Milky Way's past accretion history. For instance, the motion of halo stars and globular clusters can reveal how the Milky Way interacted with other galaxies and absorbed their material over billions of years. This can include past mergers and the relationship with smaller galaxies that may have merged with the Milky Way, contributing stars and gas to the halo. Recent research into the halo has also provided insights into the nature of dark matter. The halo's gravitational effects indicate that a significant amount of dark matter exists there, influencing the dynamics of galaxies beyond just the visible components. By studying the halo, astronomers not only gain a clearer picture of the Milky Way's history, but also acquire essential information about the broader cosmic environment in which it resides. This knowledge continues to evolve as new observational techniques and data shed light on the mysteries held within our galaxy. Galaxies like the Milky Way form and evolve through a complex process that spans billions of years beginning in the early universe. Initially, after the Big Bang, the universe was filled with a hot, turbulent sea of particles which gradually cooled and began to clump together under the influence of gravity. These early density fluctuations led to the formation of the first stars and subsequently the first galaxies. As these primordial galaxies formed, they began to interact and merge with one another. The process of mergers is fundamental to the growth of galaxies. Smaller galaxies can combine to create larger ones, leading to the structural complexity we observe today. During these mergers, gas can be funneled towards the center, igniting bursts of star formation. This phase is often accompanied by dramatic events, such as starbursts and the formation of supermassive black holes in the galactic cores, which play a significant role in the galaxy's evolution. Over time, galaxies like the Milky Way progress through various stages of evolution, influenced by factors such as star formation rates, supernovae, and the accretion of gas and dark matter. As stars within the galaxy age and die, they enrich the interstellar medium with heavy elements through processes such as supernova explosions. This enrichment fosters the formation of new stars, which can lead to the development of distinct components within the galaxy, like the central bulge, the disk, and the halo. Galaxies also interact with their environments, affecting their evolution. In the Milky Way's case, it is situated within a larger structure known as the local group, interacting with other nearby galaxies. These interactions can trigger new star formation, alter galactic morphology, and even lead to future mergers. The ongoing interplay between formation, evolution, and environmental influence allows galaxies to evolve continuously, changing shape and character over cosmic timescales, and ultimately influencing the entire structure of the universe itself. As we study galaxy formation, we uncover the dynamic history of our own Milky Way and its evolution into the massive spiral galaxy we recognize today. Nebulae are fascinating celestial objects that serve as significant indicators of the processes of star formation, evolution, and the life cycle of matter in our galaxy. In the Milky Way, there are several prominent types of nebulae, each characterized by their unique properties and roles in the cosmic environment. The most well-known type is the emission nebula, which glows brightly due to the ionization of gas by nearby young hot stars. When ultraviolet light from these stars ionizes hydrogen gas, it emits light at specific wavelengths, creating vibrant hues that often include reds and pinks. The Orion Nebula is one of the best examples of this type, providing a spectacular view of ongoing star formation. Another type, the Reflection Nebula, does not produce its light but instead reflects the light from nearby stars. These nebulae often appear blue because blue light scatters more efficiently than red light. Reflection nebulae typically accompany young stars that have yet to ionize the surrounding material. The famous nebula surrounding the star Rho Ophiuchi illustrates this beautiful phenomenon, highlighting the contrast between bright stars and the surrounding dust. Dark nebulae, in contrast, are dense clouds of gas and dust that block the light from stars and other objects behind them. They are often seen as silhouettes against the brighter background of stars or emission nebulae. The Horsehead Nebula is a well-known example of a dark nebula, showcasing how these dense regions can obscure light, yet harbor potential for future star formation within their depths. Lastly, planetary nebulae represent the later stage of a star's life cycle. When medium-sized stars exhaust their nuclear fuel, they expel their outer layers, creating a shell of ionized gas around their remnant core. The Ring Nebula is a classic example of a planetary nebula, illustrating this transitional stage before the star ultimately fades away. Each type of nebula contributes to our understanding of the galaxy's evolution, stellar life cycles, and the intricate processes that govern what happens to matter in space. Their variety and beauty make nebulae crucial components of the cosmic landscape, illuminating the dynamic nature of the universe. The interstellar medium is the vast expanse of matter that exists between the stars within a galaxy, primarily composed of gas and dust. This medium consists of about 75% hydrogen, 25% helium, and traces of other elements, including carbon, nitrogen, and oxygen. The presence of dust within the interstellar medium is crucial because it absorbs and scatters light, influencing how we observe nebulae and other celestial phenomena. The interstellar medium plays a pivotal role in the life cycle of stars, particularly in the process of star formation. When regions of the interstellar medium experience a rise in density due to gravitational instabilities or shock waves from nearby supernovae, they can lead to the formation of dense molecular clouds. These clouds, often referred to as stellar nurseries, contain vast amounts of gas and dust that are essential for creating new stars. As these dense regions contract under their own gravity, they can fragment into smaller clumps, each capable of forming individual stars. During this process, material within these clumps becomes increasingly compressed, leading to the rise in temperature and pressure at their cores. Once the conditions become suitable, nuclear fusion ignites, marking the birth of a new star. This cascade of events illustrates how the interstellar medium is not just a backdrop, but a significant player in shaping the galactic narrative. Moreover, the interstellar medium is not static, it interacts dynamically with the stars it contains. When stars form and later explode as supernovae, they release large amounts of energy and materials back into the interstellar medium, enriching it with heavier elements. This cycle of star formation, death, and material recycling is essential for the evolution of galaxies, as it contributes to the ongoing supply of raw materials for future stars. Understanding the interstellar medium and its influence on star formation helps astronomers piece together the intricate history of galaxies like the Milky Way. It reveals the interconnectedness of cosmic phenomena and offers insights into how the universe continues to evolve, underscoring the importance of these vast regions of gas and dust in the grand tapestry of the cosmos. Astronomers have developed several techniques to study the composition of stars and nebulae, primarily by analyzing the light they emit or reflect. One of the most fundamental methods used is spectroscopy, which involves splitting light into its component colors or wavelengths. By using a device called a spectroscope, astronomers can identify specific lines in the spectrum of light emitted by a star or a nebula. These lines correspond to the fingerprints of various elements and molecules, allowing scientists to determine the chemical composition, temperature, density, and other physical properties of these celestial objects. So, when light passes through a nebula or is emitted by a star, specific wavelengths are absorbed or emitted by the atoms present. Each element has a unique pattern of spectral lines, much like a barcode, which allows astronomers to identify which elements are present. For example, the presence of hydrogen can be inferred from its characteristic spectral lines, while the abundance of heavier elements such as carbon or oxygen can also be discerned using this technique. This information not only reveals the composition of those objects, but also provides insights into the processes that occurred during their formation and evolution. Astronomers also employ photometry, which involves measuring the intensity of light from a celestial object at various wavelengths. This technique can provide clues about the temperature and size of stars, as different temperatures correspond to specific colors of light emitted. By combining photometric data with spectroscopic results, astronomers can create a more comprehensive picture of a star's characteristics. Additionally, advancements in technology, such as space-based observatories, have enhanced our ability to study celestial objects across various wavelengths, including ultraviolet, infrared, and radio. Each of these observations offers unique insights into the composition and behavior of stars and nebulae. For instance, infrared observations can penetrate dense clouds of dust, allowing astronomers to study regions of star formation that would otherwise be obscured in optical wavelengths. Through the integration of these methods, astronomers continue to unravel the complexities of the universe. The study of stellar and nebular composition not only enhances our understanding of individual objects, but also sheds light on the broader processes governing galaxy formation, chemical evolution, and the life cycle of matter in the cosmos. Stellar nurseries are regions in space where new stars are born, characterized by dense clouds of gas and dust known as molecular clouds. These areas serve as the primary sites of star formation within the Milky Way galaxy. The conditions in stellar nurseries are often ripe for creating new stellar objects, as the gas and dust gather and contract under gravitational forces, leading to the formation of protostars. These protostars eventually evolve into fully fledged stars, contributing to the ongoing cycle of star formation in the galaxy. In the Milky Way, stellar nurseries can be found in various locations, often concentrated in spiral arms where the density of gas and dust is higher. One of the most famous examples is the Orion Nebula, located in the Orion constellation. It is easily visible to the naked eye and serves as a rich laboratory for observing star formation in action. The nebula is filled with young, luminous stars and is a prime site for protostars to develop. Another notable stellar nursery is the Lagoon Nebula, found in the constellation Sagittarius. This region is not only a site of ongoing star formation, but also home to many young star clusters. Similarly, the Carina Nebula, located in the southern sky, showcases impressive amounts of star formation and hosts some of the most massive stars known. Stellar nurseries can also be found in association with giant molecular clouds scattered throughout the galaxy. These clouds are often found in regions of active star formation, such as the densest parts of spiral arms, or in areas influenced by previous star formation events, like supernova explosions. The interactions between stars and the interstellar medium in these environments create the conditions necessary for subsequent generations of stars to form. The investigation of stellar nurseries is vital for understanding the life cycle of stars and their impact on the evolution of galaxies. By studying these remarkable regions, astronomers gain insights into the processes that govern star formation, the birthplaces of stellar populations, and the formation of planetary systems around new stars. Supermassive black holes are colossal gravitational entities located at the centers of most large galaxies, including our own Milky Way. These black holes, with masses ranging from millions to billions of times that of the Sun, exert a profound influence on their host galaxies, and play a critical role in their evolution. Their effects extend far beyond their immediate vicinity, impacting star formation, galaxy structure, and even the dynamics of entire galactic systems. One significant way supermassive black holes influence galactic evolution is through feedback mechanisms. As material such as gas and dust falls into the black hole, it can form an accretion disk, an extraordinarily hot and energetic disk of material spiraling inward. The intense gravitational forces and energy released in the form of radiation can produce powerful outflows and jets. These outflows can heat surrounding gas, preventing it from collapsing to form new stars, effectively regulating star formation rates in the galaxy. This feedback loop is crucial in shaping the overall star formation history and evolution of the galaxy. Additionally, the presence of a supermassive black hole can affect the motion of stars and gas in the galactic core. The gravitational pull from the black hole influences the orbits of nearby stars and can lead to complex interactions that contribute to the dynamics of the central region. This can help maintain the structure of the galaxy as stars are drawn into stable orbits around the black hole, forming a central cluster. Moreover, the growth and evolution of supermassive black holes themselves are intricately linked to the evolution of their host galaxies. As galaxies merge, their central black holes can also draw closer together, eventually coalescing into a single, more massive supermassive black hole. These mergers can have significant impacts on the surrounding galactic environment, leading to bursts of star formation and altering the overall morphology of the galaxy. Finally, supermassive black holes can influence the distribution of dark matter and the gravitational landscape of the galaxy. Their presence can affect how dark matter halos evolve and interact with the baryonic matter in the galaxy, shaping the entire galactic ecosystem. Studying these enigmatic entities is crucial for understanding the broader processes governing galaxy formation and evolution. Supermassive black holes are not merely endpoints of stellar evolution, but are active participants in the intricate dance of cosmic evolution, linking the fates of galaxies and their central cores in our ever-expanding universe. Galaxy mergers are fascinating cosmic events where two or more galaxies collide and amalgamate under the influence of their gravitational attraction. These mergers can vary in scale and complexity, ranging from small dwarf galaxies merging with larger ones to significant collisions between massive spiral galaxies. The process can take millions to billions of years, leading to dramatic changes in the structure and composition of the involved galaxies. The Milky Way is on a collision course with the Andromeda Galaxy, the closest spiral galaxy, which will have profound implications for our galaxy's future. When these two galaxies eventually merge, expected to occur in about 4 billion years, the gravitational interactions between them will induce significant structural changes. The collision will likely trigger bursts of star formation due to the compression of gas and dust as their interstellar media interact. This process can lead to the birth of new stars from the gas that becomes densely packed in certain regions. During the merger, the stars themselves are unlikely to collide, given the vast distances between them. However, their orbits will be profoundly affected, potentially leading to new galactic structures. The Milky Way and Andromeda will likely lose their distinct identities and gradually form a new elliptical galaxy over time. The merging process will also lead to the formation of a supermassive black hole at the center of the new composite galaxy, as the black holes embedded within each original galaxy draw together and coalesce. The collision will also reconfigure the distribution of dark matter and shape the gravitational landscape within the newly formed galaxy. This restructuring may influence the orbits of remaining stars, dark matter distribution, and even the formation of new galactic subsections or structures, such as tidal tails, which are streams of stars and gas that can extend outward from the merging galaxies. While this cosmic collision may seem catastrophic, it is part of the natural cycle of galaxy evolution. Understanding galaxy mergers equips astronomers with insights into how galaxies grow and evolve over cosmic timescales. The Milky Way's impending merger with Andromeda serves as a reminder of our galaxy's dynamic nature and the ongoing processes that shape the universe, illustrating that even colossal systems are subject to change and transformation as they traverse the cosmic landscape. Gamma-ray bursts are among the most powerful and energetic explosions observed in the universe, releasing immense amounts of energy in the form of gamma rays. These bursts can last from a fraction of a second to several minutes, and they are thought to originate from two primary types of astronomical events: the collapse of massive stars into black holes, often accompanied by supernovae, and the merger of binary neutron stars or neutron star black hole systems. The intense energy emitted during a gamma-ray burst can have profound implications for its surrounding environment. When a burst occurs, the gamma rays travel vast distances through space, and if they are directed toward a galaxy, they can impact the interstellar medium. This impact can ionize gas, compress surrounding material, and trigger waves of star formation by triggering shock waves that compress gas clouds into regions where new stars can form. One of the more dramatic potential effects of a gamma-ray burst is its capacity to irradiate nearby stars and planets. If a gamma-ray burst were to occur close to our galaxy, such as within a few thousand light-years, it could expose the outer layers of nearby celestial bodies to harmful radiation. This radiation could severely impact any existing life forms or disrupt the atmospheric chemistry of planets, potentially leading to mass extinctions or altering biospheres on those planets. Moreover, frequent gamma-ray bursts occurring in the galaxy's history might indicate areas of active star formation and cosmic arms. Their study helps astronomers understand the conditions leading to extreme stellar evolution and provides insights into the processes that shape galactic dynamics. Gamma-ray bursts serve as cosmic beacons that suggest the violent and dynamic nature of the universe. By studying these phenomena, astronomers can gain insights into the life cycles of massive stars, the behavior of extreme conditions, and the complex interactions that occur within galaxies. Understanding these bursts also sheds light on the potential impact of such extraordinary events on the history and evolution of galaxies like our Milky Way. Supernovae are explosive events that mark the death of massive stars, and they play a crucial role in the evolution of the Milky Way galaxy. As these stars reach the end of their life cycles, they expel their outer layers into space with tremendous force, creating shock waves that significantly impact their surroundings. Supernovae contribute to the galactic ecosystem in several important ways. One primary effect of supernovae is the enrichment of the interstellar medium with heavy elements. During their life cycles, massive stars forge elements such as carbon, oxygen, and iron through nuclear fusion. When a supernova occurs, these elements are released into the surrounding gas and dust, significantly enriching the interstellar medium. This process of chemical enrichment is fundamental for subsequent generations of stars, as it allows for the formation of planets and the basic building blocks of life. Without the contribution from supernovae, the universe's elemental diversity would be severely limited. Furthermore, the shock waves generated by supernova explosions can trigger new star formation. As the expelled material collides with surrounding gas clouds, it compresses them, creating regions where density increases. This can lead to the collapse of these clouds and the birth of new stars. Thus, supernovae act as agents of stellar recycling, fostering the continuous cycle of star formation within the Milky Way. Supernovae also influence the dynamics and structure of the galaxy. The energy released during an explosion can create supernova remnants, which are often observed as nebulae of glowing gas and dust. These remnants can create turbulence within the interstellar medium, affecting how gas moves and flows through the galaxy. This turbulence can impact the gravitational interactions within the Milky Way, shaping its overall structure over time. Additionally, supernovae play a role in shaping the fate of star clusters. When a massive star in a cluster explodes, the dynamics of the remaining stars may be altered, potentially leading to the disruption of the cluster itself. These events can enhance the gravitational interactions within the cluster, contributing to its long-term evolution. Supernovae are crucial contributors to the Milky Way's evolutionary narrative. They enrich the interstellar medium with essential elements, trigger new star formation, and influence the galactic dynamics and structure. Their effects are integral to understanding the ongoing processes that shape our galaxy, illustrating the interconnectedness of stellar life cycles and the broader cosmic environment. Magnetars are a type of neutron star, and they are among the most extreme objects in the universe due to their incredibly powerful magnetic fields and immense energy output. A neutron star is the remnant core of a massive star that has exploded in a supernova, collapsing under gravity to a point where protons and electrons combine to form neutrons. Magnetars, a subset of neutron stars, possess magnetic fields that are approximately 1,000 times stronger than that of an ordinary neutron star and can be up to 1 trillion times stronger than the Earth's magnetic field. The intense magnetic fields of magnetars play a critical role in their behavior and observable phenomena. These magnetic fields can create extreme conditions that lead to the release of energy in the form of soft gamma-ray bursts and X-rays. This activity is often attributed to the decay of the magnetic field over time, which generates tremendous amounts of energy. This energy can result in dramatic outbursts, emitting radiation that can be detected across vast distances in space. Additionally, the magnetic fields of magnetars can have profound effects on their surroundings. The extreme magnetic environment can distort the structure of nearby materials, affecting the dynamics of surrounding star systems or interstellar mediums. If a magnetar is located close enough to other stars or planets, the intense radiation and magnetic forces can ionize nearby gases or even strip away atmospheres, significantly impacting any potential habitability. The extreme nature of magnetars makes them significant for scientific study. Their unique properties challenge our understanding of stellar evolution, magnetic fields, and the fundamental physics that govern the universe. By investigating magnetars, researchers can gain insights into the processes that lead to the formation of these extraordinary objects and the role they play in the broader astrophysical context. Magnetars exemplify the fascinating diversity of celestial phenomena, showcasing how the laws of physics can create environments and objects that push the boundaries of our understanding of the universe. Their extreme nature not only highlights the inherent variability in stellar remnants, but also emphasizes the importance of continued exploration and observation in unraveling the mysteries of cosmic evolution. Cosmic rays are high-energy particles that travel through space and reach Earth from various sources, originating primarily from supernovae, active galactic nuclei, and other energetic astrophysical processes. These rays are predominantly composed of protons, but they can also include heavier nuclei, electrons, and even photons. Understanding their origins and how they traverse the galaxy provides critical insights into high-energy astrophysics and the dynamics of the universe. The most significant source of cosmic rays is believed to be supernova explosions. When a massive star exhausts its nuclear fuel and explodes, it generates shock waves that accelerate charged particles to tremendous speeds. These particles can attain energies exceeding that of particles produced in human-made particle accelerators. As supernova remnants expand, they create a turbulent environment where particles can gain energy through shockwave interactions and magnetic fields. Another source of cosmic rays comes from active galactic nuclei, which are regions surrounding supermassive black holes at the centers of galaxies. As matter falls toward these black holes, it accelerates and emits radiation across multiple wavelengths. The energetic processes occurring in these regions can also produce high-energy particles that escape into intergalactic space and enter our galaxy. Once cosmic rays are generated, their journey through the galaxy is influenced by magnetic fields present in the interstellar medium. These fields can cause the particles to travel in curved paths rather than in straight lines, making it challenging to trace their origins. Cosmic rays can interact with the gas and dust in the interstellar medium, producing secondary particles such as pions and kaons, which can cascade into even lower energy particles. Cosmic rays travel vast distances through the galaxy, often taking tens of thousands of years to traverse from their origins to our solar system. As they propagate, they may encounter regions of varying magnetic field strengths and densities, resulting in scattering and diffusion. Despite these interactions, about 1% of cosmic rays manage to reach Earth, where they can be detected by ground-based observatories and high-altitude balloon experiments. Studying cosmic rays allows scientists to probe not only the processes occurring in distant cosmic events, but also the underlying mechanisms of particle acceleration and propagation in the galaxy. Understanding these high-energy particles provides valuable insights into the extreme environments and phenomena that characterize the universe, enhancing our grasp of the intricate interplay between cosmic forces and the fabric of our galaxy. Gravitational waves are ripples in the fabric of spacetime that occur when massive objects like black holes or neutron stars accelerate. Imagine throwing a stone into a calm pond. The ripples that form on the surface represent the waves traveling outward. These gravitational waves carry information about their origins and the nature of gravity itself, providing a novel way to observe celestial events. The existence of gravitational waves was proposed over a century ago by Albert Einstein as a part of his general theory of relativity. This theory fundamentally changed our understanding of gravity, depicting it not as a force but as the curvature of spacetime caused by mass. It wasn't until the detection of gravitational waves by the LIGO Observatory in 2015 that we could confirm their presence and open a new window into the universe. Gravitational waves have significantly enhanced our comprehension of the cosmos by allowing scientists to observe events previously hidden from our view. For instance, the merging of black holes produces gravitational waves that carry details about these colossal objects, unlike anything captured by traditional telescopes. These discoveries enable physicists to test the limits of current theories about space, time, and the fundamental forces of nature. In addition to providing information about black hole collisions, gravitational waves have also helped confirm the existence of neutron-star mergers. The study of these events has led to new insights into the creation of heavy elements such as gold and platinum in the cosmos. As we refine our ability to detect and analyze gravitational waves, we continue to uncover the intricate workings of the universe and deepen our understanding of fundamental astrophysical processes. Cosmic inflation refers to a rapid expansion of the universe that is theorized to have occurred just after the Big Bang. This expansion happened in an incredibly short time frame, approximately 10 to the power of minus 36 seconds to 10 to the power of minus 33 seconds after the universe began. During this period, the universe grew exponentially, increasing in size far more than it could in a standard manner. This sudden growth helped shape the structure of the cosmos we observe today. The concept of inflation was introduced to address several puzzling problems in cosmology, including why the universe appears so flat and homogeneous on large scales. Before inflation was proposed, these characteristics were difficult to explain. By inflating the universe at such an early stage, tiny quantum fluctuations were stretched across vast distances, laying the groundwork for the density variations that would eventually lead to the formation of galaxies and clusters. Inflation also serves as a bridge connecting our understanding of the universe's earliest moments with the observable universe we see today. As the universe expanded, it cooled down, allowing fundamental particles to form, which later combined to create atoms, stars, galaxies, and other structures. This theory links the microcosmic quantum world with the macrocosmic universe, illustrating how the small fluctuations in density contributed to the larger structures we see in today's cosmos. Moreover, observations of the cosmic microwave background radiation provide compelling evidence for inflation. This relic radiation is the afterglow of the Big Bang and carries with it imprints of the conditions of the early universe. The patterns of temperature fluctuations in this radiation match the predictions made by inflationary models, further solidifying its role in our understanding of cosmic evolution. Through the lens of inflation, we gain profound insights into the origins and development of the universe as we know it. Astronomers study dark energy, the mysterious force believed to drive the accelerated expansion of the universe, by using a variety of observational techniques and tools. One of the primary methods involves analyzing the light from distant supernovae, particularly type Ia supernovae. These explosions occur in binary star systems where a white dwarf accumulates material until it reaches a critical mass and explodes. Because type Ia supernovae have a consistent peak luminosity, they serve as reliable standard candles. By measuring their brightness and redshift, astronomers can determine their distance from Earth and track the expansion rate of the universe. Additionally, astronomers observe the large-scale structure of the universe, which includes galaxy clusters and the cosmic web formed by the distribution of galaxies. By mapping the arrangements and movements of galaxies, scientists can infer the influence of dark energy on cosmic acceleration. When comparing the observed structure of the universe with simulations, they can gauge how dark energy affects gravitational dynamics and galaxy formation over time. Another important approach involves studying the cosmic microwave background radiation. This faint afterglow from the Big Bang contains clues about the universe's expansion history. Precise measurements of temperature fluctuations in this radiation can reveal information about the density and distribution of matter and dark energy throughout the cosmos. Data from missions such as the Wilkinson Microwave Anisotropy Probe and the Planck Satellite have provided valuable insights into the role of dark energy in shaping the early universe's evolution. Combining these techniques, astronomers can piece together a comprehensive understanding of dark energy's effect on galactic expansion. By measuring its rate and mapping its influence over cosmic history, researchers are progressively unraveling the mysteries of this enigmatic force, which constitutes approximately 70% of the universe. Each discovery not only advances our knowledge of dark energy, but also enhances our understanding of fundamental physics and the overall fate of the universe. Quasars, or quasi-stellar objects, are extremely luminous and distant celestial objects powered by supermassive black holes at the centers of galaxies. These black holes can weigh millions, or even billions of times more than our Sun. As matter falls into these black holes, it forms an accretion disk, generating immense amounts of energy that result in brightness far surpassing that of their host galaxies. This remarkable luminosity allows quasars to be observed over vast distances, making them key indicators of the universe's evolution. Quasars are believed to be most prevalent during a period known as the cosmic noon, roughly between 10 billion and 12 billion years ago, when the universe was much younger. During this epoch, many galaxies were undergoing significant formation and growth, often merging with one another. The increased interactions between galaxies and the inflow of gas and dust into the central supermassive black holes likely triggered quasar activity, providing a glimpse into the conditions that fostered galactic evolution. Studying quasars gives astronomers insight into the formative processes of galaxies. The energetic outflows and jets produced by the material falling into black holes can affect star formation and regulate the evolution of their host galaxies. This feedback mechanism can either suppress star formation by heating surrounding gas or trigger new star formation by compressing it, illustrating the delicate balance between a galaxy's growth and the influence of its central black hole. Remarkably, the existence of quasars also raises intriguing questions about the relationship between galaxy formation and black hole growth. Understanding how these powerful entities evolve alongside their host galaxies provides crucial clues about the history of the universe and the mechanisms driving cosmic structure formation. As astronomers continue to explore these brilliant beacons, quasars remain pivotal to unraveling the mysteries of galactic evolution and the dynamic processes that shape the cosmos. Black holes exert a profound influence on the fabric of space-time within galaxies due to their immense mass and gravitational pull. According to Einstein's general theory of relativity, gravity is not just a force but a curvature of space-time around massive objects. A black hole, with its concentrated mass typically millions or even billions of times that of our Sun, significantly warps the surrounding space-time, creating a gravitational well that affects the motion of nearby stars, gas, and dust. As objects come close to a black hole, they experience stronger gravitational forces, altering their orbits and trajectories. This interaction leads to complex dynamics within galaxies, especially in their dense cores. Stars can be pulled toward the black hole, where they may eventually spiral in and become part of the accretion disk if they stray too close. The gravitational influence of black holes can also reorder star systems, leading to the ejection of other stars into intergalactic space, known as the gravitational slingshot effect. Moreover, black holes can impact the overall evolution of their host galaxies through various feedback mechanisms. For instance, the energy released during material accretion onto a black hole can drive powerful outflows and jets, which may heat surrounding gas or expel it entirely. This heating can inhibit star formation in the galaxy by preventing cold gas from collapsing into new stars, illustrating how a black hole can regulate star formation processes on a galactic scale. The study of black holes also enhances our understanding of gravitational waves, especially during cosmic events like mergers. When two black holes collide, they can emit gravitational waves that ripple across the fabric of space-time, providing insight into the nature of these dark entities and their role within galaxies. This expanding knowledge of black holes not only deepens our comprehension of the complexities of space-time, but also highlights their integral role in shaping the universe's structure and evolution. The Milky Way, our vast home galaxy, hosts a variety of energetic events that showcase the dynamism of cosmic processes. Among the most significant are supernovae, the explosive deaths of massive stars. These remarkable events can release energy equivalent to that of an entire galaxy over a brief period. When a massive star exhausts its nuclear fuel, it can no longer support itself against gravitational collapse, leading to a cataclysmic explosion that ejects outer layers at tremendous velocities. Supernovae not only enrich the interstellar medium with heavy elements, but also facilitate star formation in surrounding regions by compressing gas and dust. Another highly energetic event within our galaxy is the phenomenon known as gamma-ray bursts. These are the universe's most powerful explosions, linked to the collapse of massive stars or the merger of compact objects, such as neutron stars. When these catastrophic events occur, they emit intense beams of gamma rays, observable across vast distances. While they are typically distant events, their detection in our galaxy would signify extreme activity, sending shockwaves through the cosmos. Additionally, black hole activity associated with the Milky Way's supermassive black hole, Sagittarius A star, also constitutes a highly energetic phenomenon. As matter spirals into this black hole, it produces intense radiation across various wavelengths, including X-rays. Occasional flares from Sagittarius A star suggest that when gas clouds encounter it, they can unleash bursts of energy, further emphasizing the violence inherent in black hole dynamics. Other energetic phenomena include the interactions between cosmic rays and the interstellar medium, which can result in high-energy particles that travel throughout the galaxy. Observations of such energetic events not only shed light on the violent processes shaping the Milky Way, but also contribute to our understanding of astrophysics and the nature of the universe itself. Each interaction and explosion offers a glimpse into the powerful forces that govern the cosmic landscape. The Milky Way's nearest galactic neighbors are primarily part of a group known as the Local Group, which comprises more than 50 galaxies. This collection includes several notable members, with the most significant being the Andromeda Galaxy and the Triangulum Galaxy. The Andromeda Galaxy, located approximately 2.5 million light-years away, is the closest spiral galaxy to our own. It contains about 1 trillion stars and is on a collision course with the Milky Way, projected to merge with our galaxy in about 4 billion years. Another nearby companion is the Triangulum galaxy, situated around 3 million light-years from Earth. This galaxy is the third largest in the local group and features a similar structure to the Milky Way. The Triangulum galaxy is home to hundreds of millions of stars and displays impressive spiral arms, making it a prime subject for study in understanding galaxy formation and evolution. In addition to these larger galaxies, several dwarf galaxies orbit the Milky Way. Among these are the large and small Magellanic Clouds, which are irregular galaxies and satellite companions located around 160,000 light-years away. These dwarf galaxies are crucial for studying the dynamics of galaxy interactions and the history of star formation, as they provide insights into how smaller galaxies can influence and contribute to the evolution of larger ones. These nearby galactic neighbors not only enhance our understanding of the Milky Way's structure and dynamics, but also offer a broader context for studying the evolution of galaxies within the ever-expanding cosmos. Interactions and future mergers with these galaxies will continue to shape the Milky Way's destiny, highlighting the interconnectedness of galaxies in the universe. The local group is a collection of more than 50 galaxies bound together by gravity, forming a small cluster within the vast universe. This group is centered around the Milky Way and encompasses various types of galaxies, including spiral, elliptical, and irregular forms. The local group provides a valuable context for studying galaxy dynamics, evolution, and interactions. Dominating the local group are the Andromeda Galaxy and the Milky Way itself. The Andromeda Galaxy, also known as M31, is the largest member, containing around 1 trillion stars and located approximately 2.5 million light-years away from us. Together, the Milky Way and Andromeda are on a collision course, projected to merge within the next 4 billion years, which will dramatically reshape both galaxies. Additional prominent members of the local group include the Triangulum Galaxy, designated M33, which is situated about 3 million light-years away. The Triangulum Galaxy is notable for its spiral structure and is the third largest in the group. Another significant category within the local group consists of dwarf galaxies, such as the large and small Magellanic Clouds, which orbit the Milky Way. The large Magellanic Cloud is approximately 160,000 light-years away, while the small Magellanic Cloud is a bit further at around 200,000 light-years from Earth. Lastly, there are several other dwarf galaxies, such as the Fornax dwarf, Carina dwarf, and Sculptor dwarf, that also contribute to the diversity of the local group. The interactions between these galaxies offer a rich field of study for astronomers, notably in understanding galaxy formation, evolution, and the gravitational forces that bind them together in this local cosmic neighborhood. The local group serves as a crucial element in the broader tapestry of the universe, helping to illuminate the processes that govern galaxy interactions and evolution. The Andromeda Galaxy, also known as M31, is often considered the Milky Way's closest counterpart, but there are notable differences and similarities between the two massive spiral galaxies. One of the most striking distinctions is their size. Andromeda is slightly larger than the Milky Way, containing about 1 trillion stars compared to the Milky Way's estimated 200 to 400 billion stars. This makes Andromeda the largest galaxy in the local group, while the Milky Way comes in second. In terms of structure, both galaxies exhibit classic spiral morphology, characterized by prominent arms filled with stars, gas, and dust. Andromeda features well-defined spiral arms, which are home to active regions of star formation. While the Milky Way also has similar structures, observational efforts using infrared and other wavelengths enhance our understanding of its spiral features, which are sometimes obscured by interstellar dust. The presence of these arms indicates both galaxies have experienced significant star formation over their lifetimes, though star formation rates may vary between the two. Another crucial difference lies in the supermassive black holes found at their centers. The Milky Way hosts Sagittarius A star, while Andromeda features a more massive central black hole known as M31 star. The characteristics of these black holes, including their masses and activity levels, shape the dynamics of their respective galaxies. Observations of Andromeda's black hole suggest it is more active than Sagittarius A star, which plays a role in influencing star formation and the overall evolution of the galaxy. Ultimately, both Andromeda and the Milky Way serve as vital studies in our understanding of galaxy formation and evolution. Their impending collision and merger, predicted to occur in about 4 billion years, will provide a unique opportunity to study the processes involved in galactic interactions and the fundamental mechanisms influencing the fates of spiral galaxies in the cosmos. This merger will lead to the creation of a new galaxy, offering astronomers further insights into the intricate dance of gravitational forces and stellar evolution over cosmic timescales. Satellite galaxies are smaller galaxies that orbit a larger, more massive galaxy, such as the Milky Way. These smaller companions are bound by the gravitational pull of the larger galaxy, and their interactions can significantly influence their evolution and structure over time. The gravitational forces between the satellite and the larger galaxy can lead to various phenomena, including tidal interactions that may strip gas from the satellite or alter its trajectory and morphology. The Milky Way hosts a number of satellite galaxies, the most prominent of which are the large and small Magellanic Clouds. These irregular galaxies are located about 160,000 and 200,000 light-years away, respectively. They are easily visible from the southern hemisphere and are of particular interest to astronomers because they provide insights into star formation and galactic dynamics. In addition to the Magellanic Clouds, there are several other confirmed satellite galaxies orbiting the Milky Way. These include the Fornax Dwarf, Carina Dwarf, Sculptor Dwarf, and Leo Fuston II, among others. Overall, there are around 30 known satellite galaxies, but astronomers believe there may be many more yet to be discovered. These satellite galaxies play a crucial role in our understanding of galaxy formation and evolution. Observing how they interact with the Milky Way helps scientists learn about the processes that govern galaxy dynamics, star formation, and the effects of gravitational interactions. Studying these smaller companions also contributes to our comprehension of dark matter, as the presence and behavior of satellite galaxies provide important clues about the mass distribution in the universe. Galaxies interact with each other through the force of gravity, resulting in a variety of phenomena that can dramatically alter their structures and star formation rates. When two galaxies come close together, their gravitational fields begin to exert forces on one another. These interactions can manifest as tidal forces, which are variations in the gravitational pull experienced by different parts of the galaxies. Tidal forces can lead to the stretching and distortion of the shapes of the galaxies, resulting in elongated structures or tidal tails that can stretch for hundreds of thousands of light years. As galaxies approach one another, they can also trigger bursts of new star formation. The gravitational interaction may compress gas and dust within the galaxies, leading to increased density in certain regions. This compression can initiate new processes that allow gas to collapse into new stars, often resulting in vibrant bursts of star formation in what is termed a starburst activity. Such events provide fertile ground for nurturing new stars while reshaping the galaxy's existing stellar populations. When galaxies interact closely, they can experience merging events, which can lead to the formation of larger galaxies. During a merger, the gravitational influences can cause gas to flow into the centers of the galaxies, which may fuel active galactic nuclei or even supermassive black hole activity at the center. These mergers can lead to a variety of outcomes, depending on the mass and type of the interacting galaxies, ranging from complete coalescence into a single galaxy to the creation of a new galaxy with a different structure and composition. It's also worth noting that gravitational interactions can strip material from one galaxy to another. This process, known as tidal stripping, can result in the smaller galaxy losing gas, stars, or other material to the larger galaxy, which contributes to the growth of the more massive galaxy. Over cosmic timescales, these gravitational interactions play a vital role in galaxy evolution, shaping the structure and distribution of galaxies across the universe, as well as influencing their star formation histories. Evidence of past galactic mergers in the Milky Way's history is found through various observational data, including the analysis of the galaxy's stellar population, its kinematics, and the structure of its halo. One clear indication of past mergers is the presence of streams of stars and globular clusters that exhibit unusual orbits around the Milky Way. These tidal streams are remnants of smaller galaxies that were gravitationally disrupted and absorbed by the Milky Way over billions of years. For example, the Gaia sausage, discovered through data from the Gaia Space Observatory, is believed to be the remnants of a disrupted dwarf galaxy that contributed a significant number of stars to the Milky Way's halo. Additionally, the chemical composition of stars provides important clues about past mergers. The Milky Way exhibits a range of metallicities, which refer to the abundance of elements heavier than hydrogen and helium in stars. As smaller galaxies merge into the Milky Way, they introduce different mixtures of elements into the galactic environment. Studies show that certain stellar populations within the Milky Way, particularly older stars in the halo and bulge, have distinctly different chemical signatures compared to stars in the Milky Way's disk, indicating that these populations likely originated from merging structures. The timing and nature of these mergers can also be inferred from models of galactic evolution based on simulations. These simulations offer insights into how the Milky Way formed and grew over time, often showing evidence of interactions with smaller galaxies, particularly between 6 and 10 billion years ago, which aligns with the current understanding of galaxy formation in the early universe. Moreover, the Milky Way's current interactions with its satellite galaxies, such as the Large and Small Magellanic Clouds, offer a glimpse into the ongoing processes of accretion and merging. These interactions are remnants of the galaxy's dynamic history, revealing the continued influence of past events on the Milky Way's structure today. Overall, the combination of stellar dynamics, chemical composition studies, and computer simulations paints a rich picture of the Milky Way's evolutionary history influenced by numerous galactic mergers. The future collision between the Milky Way and Andromeda galaxies is an event set to unfold over several billion years. The two galaxies are currently moving toward each other at a speed of about 100 kilometers per second, and they are on a collision course that is expected to reach a critical point in approximately 4 billion years. When this event occurs, it will dramatically reshape both galaxies and lead to profound changes in their structures and stellar populations. As the Milky Way and Andromeda draw closer, their gravitational interactions will first trigger a series of preliminary encounters, resulting in tidal forces that will distort their shapes. This interaction may initiate bursts of star formation as gas clouds are compressed, contributing to dazzling displays of new stars forming in regions where the gas density increases. The initial approach may also lead to the formation of tidal tails, which are extended streams of stars and gas that stretch out from both galaxies as they interact. The actual merger will occur over several stages. After their first close encounter, the galaxies will exchange material and gravitational influence, eventually spiraling around one another multiple times due to their mutual gravitational attraction. This back-and-forth dance can last for several 100 million years. Eventually, the two galaxies will pass through each other before becoming gravitationally bound, leading to a more prolonged merging process that will last over 1 billion years or more. Ultimately, the Milky Way and Andromeda will coalesce into a single larger galaxy, often referred to as Milkomeda or Milkdromeda. This new galaxy will likely take on a different structure than either parent galaxy, potentially evolving into an elliptical galaxy as the merger smoothens out the distinct spiral features that currently define both the Milky Way and Andromeda. Throughout this process, the vast distances between individual stars will minimize direct collisions, but significant gravitational interactions will reshape the galactic environment, altering star formation rates and changing the positions of stars as they settle into new orbits. These cosmic events are part of the natural life cycle of galaxies, showcasing the dynamic and ever-evolving nature of the universe. The future merger between the Milky Way and Andromeda provides a glimpse into the fate of our galaxy and highlights the interconnectedness of galaxies in the cosmic web. Galactic cannibalism and galactic harassment are two phenomena that describe how galaxies interact with and influence one another through gravitational forces, leading to significant changes in their structure and evolution. Galactic cannibalism occurs when a larger galaxy gravitationally captures a smaller galaxy, ultimately absorbing it into its structure. This process typically involves the smaller galaxy being pulled apart by the tidal forces exerted by the larger galaxy, resulting in the disruption and stripping away of stars, gas, and other materials. As the smaller galaxy is consumed, its stars may be assimilated into the larger galaxy, altering its stellar population and dynamics. A classic example of this phenomenon can be seen in the Milky Way's ongoing interaction with its satellite galaxies, such as the Large and Small Magellanic Clouds, which are gradually losing material to the more massive Milky Way. Galactic harassment, on the other hand, refers to the disruptive influence of gravitational interactions between two or more galaxies that do not necessarily lead to a full merger. In this scenario, a smaller galaxy passes close to a larger galaxy, experiencing significant gravitational forces that can distort its shape and behavior. These interactions can trigger bursts of star formation by compressing gas clouds within the smaller galaxy, or can lead to the stripping of gas and stars from its structure, making it more susceptible to further interactions or eventual absorption by a larger galaxy. Both phenomena illustrate the dynamic and often violent nature of galaxy interactions in the universe. They contribute to our understanding of galaxy evolution by demonstrating how the gravitational relationships between galaxies influence star formation rates, stellar distributions, and the overall structure of galactic systems. Ultimately, galactic cannibalism and harassment are vital processes in understanding how galaxies grow and evolve over cosmic timescales, shaping the intricate tapestry of the universe around us. Intergalactic voids are vast, mostly empty spaces in the universe that exist between galaxy clusters and groups. These voids can be millions of light-years across and contain very few or even no galaxies. They play a significant role in shaping the overall distribution of galaxies and the large-scale structure of the universe. The existence of intergalactic voids is essential for understanding the cosmic web, a vast network of filaments of galaxies and dark matter. This web consists of dense regions where clusters of galaxies are located, interconnected by these large voids. The distribution of galaxies is not uniform. Instead, it resembles a sponge-like or foam-like structure, with galaxies concentrated in clusters and filaments, while voids are where comparatively little matter exists. The gravitational effects of this arrangement lead to the formation of structures that influence how galaxies are formed and evolve. Voids can affect the trajectory and motion of galaxies. As galaxies move through the universe, their movement is not simply dictated by their immediate surroundings. The gravitational effects of nearby mass, including filaments and galaxy clusters, shape their paths. This interaction can lead to galaxies being funneled toward denser regions or influenced by the gravitational pull of neighboring structures. The presence of voids thus also creates pathways through which galaxies gravitate toward denser areas, further structuring the cosmic web. Moreover, voids can influence star formation within galaxies. Lower density areas may create conditions that lead to different rates of star formation compared to those in denser regions. Galaxies located on the outskirts of voids might experience reduced star formation due to a lack of gas infall and interactions with other galaxies, while galaxies situated in denser environments can experience bursts of star formation triggered by gravitational interactions with neighboring galaxies. Overall, Intergalactic voids are a crucial component of the universe's large-scale structure and significantly impact how galaxies are distributed throughout space. They represent the interplay of gravitational forces and matter distribution, highlighting how galaxies form and evolve within the cosmic framework. Understanding voids and their effects helps astronomers piece together the complex puzzle of cosmic evolution and the dynamics of the universe at large. The cosmic web is a vast structure that depicts the universe's large-scale organization. It resembles a gigantic tapestry woven from filaments of galaxies, dark matter, and gas, which stretches across the cosmos. This intricate network emerges from the attraction of gravity acting upon matter. It reveals how galaxies are distributed in the universe, forming clusters around dense nodes and connecting through long filaments in a pattern that is both beautiful and essential for our understanding of cosmic evolution. At the heart of the cosmic web are clusters of galaxies that are more densely populated. These clusters are often surrounded by less dense regions of space. Connecting these clusters are sprawling filaments filled with dark matter and gas, which play a crucial role in galaxy formation and movement. As galaxies traverse these filaments, they can accumulate more mass and interact with neighboring galaxies, leading to complex behaviors such as merging and the exchange of gas. This process is vital for the growth and evolution of galaxies over billions of years. Beyond just connecting galaxies, the cosmic web influences the cosmic microwave background radiation, the relic radiation from the Big Bang. The uneven distribution of matter in the cosmic web contributes to tiny temperature fluctuations in this ancient light, providing clues about the early universe's conditions and the properties of dark matter. Understanding these connections helps scientists decipher the fundamental laws governing the cosmos. The very fabric of the universe hinges on the intricate web connecting galaxies. This structure is a testament to the interplay between gravity, dark matter, and the forces that shape everything we see. As our technology and observational techniques advance, we continue to uncover new layers of the cosmic web, revealing further complexities and mysteries that challenge our comprehension of the universe. White dwarfs are the remnants of stars that have exhausted the nuclear fuel necessary for fusion. After a star, similar in size to our Sun, reaches the end of its life cycle, it sheds its outer layers, creating a beautiful shell of gas known as a planetary nebula. What remains is the hot core, which when it cools down becomes a white dwarf. These stellar remnants are incredibly dense, containing about the mass of the Sun compressed into a volume similar to that of Earth. This extraordinary density results in extreme gravitational forces and a lack of nuclear activity. In terms of stellar evolution, white dwarfs serve as crucial indicators of the life cycle of stars. They typically form from stars that fall into the category of low to medium mass stars, which constitute the majority of stars in our universe. Their evolution tells us much about the processes that govern stellar life and death. Initially, white dwarfs are very hot and shine brightly due to residual thermal energy, but over billions of years they gradually cool and fade. Additionally, white dwarfs play a significant role in understanding cosmic events. If a white dwarf is part of a binary system, it may accumulate matter from its companion star, which can lead to dramatic outcomes. If enough mass is acquired, the white dwarf may undergo a cataclysmic explosion known as a supernova-type ire. This event becomes an important tool for astronomers, as the uniform brightness of these supernovae helps measure cosmic distances and has even led to the discovery of the universe's accelerating expansion. The study of white dwarfs not only enriches our understanding of star formation and evolution, but also enhances our knowledge of the universe's development. As we observe these fascinating celestial objects, we glean insights into the past and future of the cosmos, making white dwarfs significant players in the complex narrative of stellar evolution. Pulsars are highly magnetized, rotating neutron stars that emit beams of electromagnetic radiation out of their magnetic poles. A neutron star is the remnants of a supernova explosion, where the core collapses under immense pressure, resulting in a compact object that is incredibly dense. A sugar cube-sized amount of neutron star material could weigh as much as a mountain. As a pulsar spins, if the beam of radiation sweeps across Earth, it is detected as pulses of radio waves, much like the flashing light of a lighthouse. These pulses occur at very regular intervals, often ranging from milliseconds to several seconds. The precise timing of these pulses is one of the most remarkable aspects of pulsars. This regularity allows astronomers to use them as cosmic clocks, helping to measure time with extraordinary precision. The pulses can reveal information about the star's rotation, magnetic field, and even the effects of relativistic physics near such massive objects. The most rapidly spinning pulsars, known as millisecond pulsars, can have rotation periods of just a few milliseconds, demonstrating incredible kinetic stability. Pulsars hold great significance for astronomers for several reasons. They can help in the study of fundamental physics, including tests of general relativity. Observations of binary systems containing pulsars have provided evidence for the existence of gravitational waves, ripples in space-time produced when massive objects accelerate, as predicted by Einstein's theory. Moreover, pulsars can assist in mapping the distribution of matter in our galaxy and beyond. Additionally, by using pulsars as cosmic beacons, astronomers can explore extreme environments and probe theories of dense matter and nuclear physics. The information gathered from pulsar observations contributes to our understanding of the evolution of stars and the structure of the universe. Thus, pulsars not only enhance our knowledge of cosmic phenomena, but also serve as vital tools in uncovering the laws of nature itself, making them key subjects of interest in contemporary astrophysical research. Stellar black holes are regions in space where gravity is so intense that nothing, not even light, can escape their grasp. These black holes form from the remnants of massive stars that undergo gravitational collapse at the end of their life cycles. When a star with a core mass greater than approximately 3 solar masses exhausts its nuclear fuel, it can no longer support itself against its own gravitational pull, leading to a catastrophic implosion, often resulting in a supernova explosion. During this supernova phase, the outer layers of the star are expelled into space, enriching the surrounding environment with heavy elements. The core, however, collapses to an extremely dense state, where the force of gravity overwhelms all other forces. If the remaining core's mass is sufficient, it can collapse to a point of infinite density known as a singularity, creating a stellar black hole surrounded by an event horizon. This event horizon acts as a boundary. Once anything crosses it, it cannot escape the black hole's gravity. The formation of stellar black holes is a critical process in the life cycle of massive stars. As these black holes form, they can have profound effects on their surroundings, including the release of energy in the form of jets or X-rays when they accrete material from a companion star or surrounding gas. This energy output can be incredibly bright, making black holes detectable even over vast distances. The existence of stellar black holes also plays a significant role in understanding galaxy evolution and the dynamics of the universe. By studying these enigmatic objects, astronomers gain insight into the processes that govern star formation and death, as well as the predictions of general relativity. Stellar black holes serve as laboratories for testing our understanding of the fundamental laws of physics, illuminating the complexities of the cosmos. Binary systems containing a black hole consist of 2 stars or celestial objects, one of which is a black hole. When a black hole is part of such a system, it can exert significant gravitational influence on its companion star. This interaction leads to unique behaviors and phenomena that are fascinating for astronomers to study. The black hole can pull material from its partner star, especially if that star extends beyond its Roche limit, leading to the formation of an accretion disk. As the material from the companion star spirals toward the black hole, it accelerates and heats up, emitting X-rays and other forms of radiation in the process. This radiation can become incredibly bright, allowing astronomers to detect black holes that are otherwise invisible. The intense energy output from the accretion process enables scientists to observe black holes indirectly and study their properties. These systems can present some of the most luminous objects in the universe, providing insights into the nature of black holes and their interactions with matter. Additionally, binary systems can offer important clues about the life cycles of massive stars. When a massive star in a binary system evolves and becomes a black hole, the companion star may also undergo significant changes in response. For instance, the interaction can strip away layers of the companion star, altering its evolutionary path. This can lead to complex dynamics, such as mass transfer between the two stars, which can influence their lifetimes and ultimate fates. Moreover, the study of binary black hole systems has revealed intriguing predictions from general relativity, particularly when these black holes interact and potentially merge. Such mergers emit gravitational waves that ripple through space-time, providing a new avenue of observation in astrophysics. Observatories around the world are now equipped to detect these faint signals, opening up a new chapter in our understanding of cosmic events and the nature of gravity itself. Consequently, binary systems containing black holes are not only vital for studying stellar evolution, but also for advancing our knowledge of the fundamental principles that govern the universe. A Wolf-Rayet star is a rare and peculiar type of massive star that is in a late stage of its evolution. These stars are characterized by their strong stellar winds and distinctive spectral features, particularly the presence of broad emission lines of helium and nitrogen. With masses typically ranging from 20 to 100 times that of the Sun, these stars burn their nuclear fuel at an extremely rapid rate and are distinguished by their intense and energetic output, far surpassing typical stars. This uniqueness arises from their complex evolutionary processes, which often precede supernova explosions. What makes Wolf-Rayet stars truly exotic is their ability to shed vast amounts of mass through powerful stellar winds. These winds can be several million times stronger than those of ordinary stars, carrying away material at incredible speeds. This mass loss can strip the star of its outer hydrogen layer, exposing its hot, helium-rich core. This core is typically much hotter than that of less massive stars, with surface temperatures reaching up to 100,000 degrees Celsius or more. The extreme conditions and composition of Wolf-Rayet stars allow them to serve as crucial laboratories for understanding the life cycles of massive stars. They play a significant role in stellar nucleosynthesis, creating heavy elements such as carbon, nitrogen, and oxygen through nuclear fusion processes. When these stars eventually undergo supernova explosions, they eject these heavy elements into the interstellar medium, enriching it and contributing to the formation of new stars and planets. Wolf-Rayet stars are also important for studying the evolution of massive stars, particularly in relation to gamma-ray bursts and the formation of black holes. Their explosive deaths are often linked to the formation of such phenomena, providing essential clues about the end stages of stellar evolution. As such, these exotic stars are a key component of our understanding of the cosmos, revealing secrets about the life cycle of massive stars and the processes that shape the universe. Planetary nebulae are beautiful, glowing shells of gas and dust ejected by stars as they approach the end of their life cycles. This phenomenon occurs in low to intermediate mass stars, such as those comparable to our Sun. After exhausting their hydrogen fuel, these stars undergo a series of transformations. Initially, they expand into red giants, during which they burn helium and other heavier elements. Eventually, the outer layers cannot be held by the star's gravitational pull and are expelled into space, forming the nebula. The formation of a planetary nebula typically involves a more complex process. As the star evolves, it experiences pulsations that help to shed its outer layers. This ejected material interacts with the surrounding interstellar medium, leading to a rich array of colors and structures in the nebula due to ionization from the hot core of the dying star. The core itself becomes a white dwarf, which is the remnant of the star, and the nebula can glow for thousands of years as it expands and cools. Planetary nebulae are important because they offer profound insights into the process of stellar death and the recycling of material in the universe. The expelled gas contains essential elements like carbon, nitrogen, and oxygen, which are synthesized during the star's life. When these elements are released into the interstellar medium, they contribute to the formation of new stars, planets, and potentially life itself. The study of planetary nebulae allows astronomers to better understand the late stages of stellar evolution. The composition, structure, and dynamics of these nebulae provide clues about the progenitor stars and the conditions under which they developed. By examining the nebulae, researchers can learn about the processes that govern mass loss in stars and how these processes shape the chemical evolution of galaxies. Therefore, planetary nebulae are not just stunning astronomical objects. They are also key to understanding the life cycles of stars and the continuous transformation of matter in the cosmos. X-ray binaries are fascinating astronomical systems comprising a pair of stars, one of which is a compact object, a neutron star or black hole, that exhibits intense X-ray emission as it interacts with its companion star. These systems are typically categorized into two main types: hard X-ray binaries and soft X-ray binaries, based on the energy of the emitted X-rays and the nature of the compact object involved. The presence of these stellar pairs leads to unique and complex interactions that generate high-energy radiation. The emission of high-energy X-rays in these systems occurs through a process known as accretion. In a binary system, the more massive compact object can exert significant gravitational pull on its companion star. If the companion star expands or is otherwise disrupted, material from its outer layers is drawn towards the compact object. As this gas spirals inwards, it forms an accretion disk around the compact object. The intense gravitational forces at play cause the infalling material to accelerate and heat up, reaching extremely high temperatures, often in the millions of degrees. This process converts gravitational potential energy into thermal energy, resulting in the emission of X-rays as the hot material radiates away some of its energy. In addition to the accretion process, the environment around these compact objects can amplify the radiation emitted. For instance, neutron stars can have extremely strong magnetic fields, leading to the acceleration of charged particles that emit X-rays via synchrotron radiation. Moreover, in some cases, events like explosive outbursts or jets can produce high-energy radiation, contributing further to the X-ray emissions that characterize these systems. X-ray binaries are essential for understanding various astrophysical phenomena, including the formation and evolution of neutron stars and black holes. They also provide insights into the dynamics of binary star systems and the effects of high-energy environments on ordinary matter. By monitoring X-ray binaries, astronomers can learn about the life cycles of stars, the nature of gravitational interactions, and the mechanics of high-energy astrophysics, making these systems significant in the study of the universe. Astronomers detect and study gravitational waves from merging black holes using highly sensitive instruments known as interferometers. The most prominent of these is the Laser Interferometer Gravitational Wave Observatory, commonly referred to as LIGO. These detectors are designed to measure incredibly tiny distortions in spacetime. Gravitational waves, created by cataclysmic events like merging black holes, cause ripples in spacetime that stretch and compress space as they pass through. The operation of interferometers involves splitting a laser beam into two perpendicular paths. These beams travel down long, evacuated tubes, reflect off mirrors, and return to a central point. When a gravitational wave passes through, it affects the distances that the beams travel, causing a change in their interference pattern. This shift can be minuscule, on the order of 1,000th the width of a proton, yet LIGO and similar observatories are equipped to detect such faint signals thanks to advanced technology and instrumentation. When LIGO makes a detection, a series of analysis steps follow to confirm and study the event. The first step is to rule out noise from other sources, ensuring that the signal is indeed a gravitational wave and not an artifact. Once confirmed, astronomers can measure properties of the black hole merger, such as the masses of the black holes, the distance to the event, and the energy released during the collision. These data allow researchers to build a comprehensive picture of the event and enhance our understanding of black hole formation and the dynamics of their mergers. Further observations often involve multi-messenger astronomy, where gravitational wave detections are combined with electromagnetic signals from the same event, such as gamma-ray bursts or kilonovae. This interdisciplinary approach expands the richness of data available, providing insights into the processes occurring during black hole mergers and the fundamental nature of gravity itself. As gravitational wave astronomy continues to evolve, it promises to unveil even more about the universe, allowing us to explore cosmic phenomena previously undetectable. Supernovae, the explosive deaths of stars, are classified into several types based on their progenitors and mechanisms of explosion. The two primary categories are Type 1 and Type 2 supernovae. Type 1 supernovae occur in binary systems where one star is a white dwarf. When the white dwarf accretes enough matter from its companion star, it can reach a critical mass, leading to a thermonuclear explosion that completely disrupts the star. This type is significant in determining cosmic distances due to its consistent brightness and is often used as a standard candle in cosmology. On the other hand, Type 2 supernovae arise from the core collapse of massive stars, typically those with more than 8 solar masses. As these stars exhaust their nuclear fuel, their cores implode under gravity, leading to a rebound effect that results in a spectacular explosion. The outer layers are ejected into space, enriching the surrounding region with heavy elements formed during the star's life. Both types of supernovae play crucial roles in galactic chemistry. When they explode, they release vast quantities of elements into the interstellar medium, including heavy elements like carbon, oxygen, and iron, which are created through the fusion processes within the stars. These newly synthesized elements are essential for the evolution of future generations of stars and planets. For instance, the oxygen and carbon produced in supernova become integral components of the molecular clouds that eventually collapse to form new stars. The distribution of these elements influences the dynamics and chemistry of galaxies. Supernovae can trigger the formation of new stars by compressing nearby gas clouds, leading to increased star formation activity. Additionally, the shock waves from the explosions can help disperse and mix materials across the galaxy, fostering a rich mosaic of chemical diversity. This process is pivotal for understanding the chemical evolution of galaxies over cosmic time, revealing how the universe transitions from the primordial hydrogen and helium produced in the Big Bang to the complex chemistry required for life. Thus, supernovae are not simply destructive events. They are fundamental to the cycle of matter and the very fabric of cosmic evolution. Astronomers study stellar remnants such as white dwarfs, neutron stars, and black holes to unravel the history of the Milky Way galaxy. These remnants serve as cosmic fossils, providing valuable insights into the processes that shaped the galaxy over billions of years. By analyzing their properties, researchers can learn about the formation, evolution, and dramatic events that have taken place within our galactic home. One of the key ways stellar remnants contribute to our understanding of galactic history is through their ages and compositions. For instance, white dwarfs, which represent the final stages of low to intermediate mass stars, can be used to estimate the ages of star clusters. By determining how long it takes a white dwarf to cool down after its formation, astronomers can estimate the age of the cluster. Different types of star clusters, such as open clusters and globular clusters, tell distinct stories about star formation and the dynamical evolution of our galaxy. Neutron stars and black holes also provide critical information about the life cycles of massive stars in the Milky Way. By studying pulsars, rapidly rotating neutron stars emitting beams of radiation, scientists can gain insights into the distribution of massive stars in the galaxy and observe phenomena like gravitational waves produced by merging black holes. Moreover, the remnants of supernova explosions enrich the interstellar medium with heavy elements that contribute to the chemical evolution of the galaxy. These elements are fundamental for understanding star formation rates and the conditions that foster the development of new stars and planets. Additionally, stellar remnants can reveal the history of interactions and mergers between different components of the Milky Way. For example, the presence of certain types of stars or specific chemical abundances can indicate past accretion events, where the galaxy absorbed smaller satellite galaxies. This history of accretion and merger events has significant implications for the structure and dynamics of the Milky Way today. Through the careful study of stellar remnants, astronomers piece together the intricate tapestry of the Milky Way's history. These remnants do not merely signify the end of a star's life, they embody the evolutionary milestones of the galaxy, offering a clear lens through which the past can be explored and understood. The Great Attractor is a massive gravitational anomaly located in the direction of the constellations Centaurus and Hydra. At the heart of this region lies a concentration of mass that exerts a significant gravitational pull on galaxies, influencing their motion over vast cosmic distances. While the exact nature and composition of the Great Attractor are still subjects of research, it is generally understood to be an area that encompasses a large number of galaxy clusters, including the Norma cluster, along with considerable dark matter. The Great Attractor influences galactic motion primarily through its gravitational force. Galaxies that are relatively close to this region, including parts of the Milky Way and our neighboring galaxies, experience an acceleration toward it. This results in a peculiar motion of these galaxies, often referred to as flows. These flows reveal a coherent pattern that indicates that multiple galaxies are not just moving randomly, but are instead being drawn towards a common center of mass, an influence that can be traced over distances of several 100 million light-years. One intriguing aspect of the Great Attractor is its relationship with the larger cosmic structures. It is part of a more extensive gravitational network beyond our local group of galaxies, which also includes the local supercluster. This hierarchical structure has far-reaching implications for the distribution of galaxies and clusters throughout the universe, showing how mass distribution influences cosmic evolution. The existence and influence of the Great Attractor challenge our understanding of the cosmos and the forces at play beyond what visible matter can account for. Much of the mass contributing to the Great Attractor is believed to be in the form of dark matter, an invisible substance that comprises a significant portion of the universe's total mass. By studying the dynamics of galactic movements in relation to this massive gravitational entity, astronomers gain vital insights into the behavior of galaxies, as well as the mysterious nature of dark matter and the overall large-scale structure of the universe. The unexpected rotation curves of galaxies are a fascinating aspect of astrophysics that challenges our understanding of gravity and the distribution of mass in the universe. Observations reveal that the outer regions of galaxies rotate much faster than would be predicted by the visible matter alone. According to the laws of gravity, we would expect that the orbital speeds of stars and gas would decline with distance from the galactic center, similar to how planets in the solar system move slower as they are further from the sun. However, what astronomers observe is a relatively flat rotation curve, indicating that stars at the outer edges of galaxies move at high speeds. The primary explanation for these unexpected rotation curves is the presence of dark matter. Dark matter is an unseen substance that does not emit, absorb, or reflect light, making it difficult to detect directly. However, its gravitational effects are evident through the motions of stars and gas in galaxies. It is believed that a significant amount of dark matter exists in halos surrounding galaxies, extending well beyond the visible components. This dark matter halo adds additional mass, exerting gravitational forces that keep the stars in the outer regions moving at higher speeds than would be expected based solely on the visible matter such as stars, gas, and dust. Another contributing factor to the rotation curves is galaxy formation history, which involves the merging and interactions of galaxies over time. These processes can lead to the redistribution of both visible and dark matter within galaxies, potentially influencing how mass is distributed and how stars are affected by gravitational interactions. The implications of these unexpected rotation curves are far-reaching, prompting critical questions about the nature of dark matter and the overall dynamics of galaxies. The continued study of galactic rotation curves not only helps astronomers refine their models of galaxy structure and formation, but also sheds light on the fundamental composition of the universe, revealing a complex interplay between visible matter and the elusive yet abundant dark matter that shapes the cosmos. The missing baryon problem refers to a significant discrepancy between the amount of baryonic matter, composed of protons, neutrons, and electrons, that astronomical observations predict should exist in the universe, and the amount of baryonic matter that is actually accounted for through direct detection. When scientists assess the total baryonic content based on observations of galaxies, clusters, and cosmic microwave background radiation, they find that only about half of the expected baryonic matter is visible in stars, galaxies, and intergalactic gas. This leaves a substantial portion of baryons seemingly unaccounted for, creating a mystery in cosmology. Several hypotheses have been proposed to explain this missing baryonic matter. One key idea suggests that much of it may be lurking in the form of diffuse gas that is too faint to detect with current observational methods. This gas could reside in the vast cosmic voids, existing at temperatures ranging from a few thousand to millions of degrees. When this gas is not ionized or sufficiently concentrated, it becomes extremely challenging to observe, leading to the impression that it is missing. Another possibility is that baryons may be in the form of cold and warm gas clouds throughout the intergalactic medium. These could have formed during cosmic structure formation and reside between galaxies, contributing to the overall baryon budget without being directly observable. Furthermore, theoretical models suggest that some baryonic matter might be hidden in non-luminous objects, such as rogue planets or brown dwarfs, which do not shine brightly enough to be detected with current instrumentation. Additionally, studies of galaxy formation and evolution indicate that baryonic matter might be cycling in and out of galaxies through various processes, including supernova explosions and galactic winds. These events can eject gas and dust into the intergalactic medium, making it difficult to trace the baryons' original locations. Addressing the missing baryon problem continues to be a major focus of research in astrophysics. As observational technologies improve and more sophisticated simulations of cosmic structure formation are developed, astronomers are hopeful that they will uncover the hidden baryonic matter. Understanding this missing component is crucial for a complete picture of the universe's composition and for refining models of cosmic evolution, providing deeper insights into the workings of the cosmos. Dark energy is a mysterious form of energy that permeates all of space and is believed to be responsible for the accelerated expansion of the universe. It accounts for approximately 70% of the total energy density of the cosmos, yet its exact nature remains one of the most profound unsolved problems in modern cosmology. Unlike matter, which can clump together under the influence of gravity, dark energy appears to exert a repulsive force, driving galaxies apart and causing the expansion of the universe to accelerate over time. The effects of dark energy were first inferred from observations of distant supernovae in the late 20th century. Researchers noticed that these supernovae were dimmer than expected, suggesting they were farther away than previously thought. This observation implied that the expansion of the universe is not only continuing, but also speeding up, contradicting the earlier belief that gravitational forces would slow the expansion over time. This dramatic shift in understanding led to the widespread acceptance of the existence of dark energy as a driving force in the cosmos. Cosmologists often model dark energy using a concept called the cosmological constant, which originated from Einstein's theory of general relativity. In this framework, dark energy does not evolve or change as the universe expands. Its energy density remains constant. However, other theories propose that dark energy could belong to a dynamic field with properties that evolve over time, known as quintessence. Despite the various theories, the fundamental characteristics of dark energy remain elusive. The influence of dark energy on galactic expansion has profound implications for the fate of the universe. Under the influence of dark energy, galaxies are expected to continue moving away from each other at an accelerating rate. This means that over billions of years, distant galaxies will recede beyond the observable universe, resulting in a future where the night sky will be devoid of most of the galaxies we see today. Understanding dark energy is crucial not only for clarifying the current state of the universe, but also for predicting its ultimate fate. As research continues, scientists aim to unveil the true nature of dark energy, which could reshape our understanding of the cosmos and the fundamental forces at play. The Milky Way is surrounded by a number of satellite galaxies, but many astronomers have noted an apparent lack of smaller satellite galaxies, which can be a puzzle. Current observations reveal over 50 smaller satellite galaxies, but models of galaxy formation would suggest that there should be many more. This discrepancy leads scientists to explore various explanations. One compelling theory revolves around the gravitational influence of the Milky Way itself. The larger gravitational pull of the Milky Way may strip away the gas and stars from smaller galaxies as they approach. This process, known as tidal stripping, can cause these smaller systems to lose their material and ultimately become difficult to detect. This means that the satellites might have been present at one time, but have since been disrupted or diminished. Another aspect that comes into play is the concept of feedback from star formation. In smaller galaxies, the energy and radiation from young stars can blow away gas, leading to the inability to form new stars and potentially causing these galaxies to fade away. This phenomenon may inhibit the formation of many smaller satellites in the first place, especially in the environments influenced by larger neighbors like the Milky Way. Astrobiologists have also considered the possibility that the formation of small galaxies is affected by cosmic reionization. After the Big Bang, the universe underwent a period of reionization that heated up and ionized the gas. This event could have limited the formation of smaller structures during a crucial time in the universe's development, contributing to the lower observable numbers surrounding large galaxies like ours. As researchers continue to investigate these dynamics, new insights may emerge, helping to clarify the intriguing story of our galaxy's satellite companions. High-velocity clouds, or HVCs, are fascinating structures found in the galactic halo, and their origins have sparked considerable investigation among astronomers. These clouds consist of hydrogen gas moving at speeds significantly differing from the more orderly rotation of the Milky Way. As we look at them, their presence suggests dynamic processes occurring in our galaxy's environment. Several hypotheses have been proposed to explain the origin of these clouds. One prominent idea is that HVCs are remnants of past interactions with nearby galaxies. As smaller galaxies or intergalactic gas clouds merge or collide with the Milky Way, they can create these high-velocity clouds. The interactions might impart significant kinetic energy to the gas, causing it to accelerate and appear as HVCs in the vast halo surrounding our galaxy. Another possibility is that these clouds could be primordial, meaning they formed shortly after the Big Bang. They might represent regions of gas that failed to coalesce into stars or larger structures, remaining as isolated high-velocity entities. These primordial clouds could contain materials essential for future star formation and influence the evolution of the Milky Way as they interact with its gravitational field. Furthermore, some researchers suggest that high-velocity clouds could originate from processes occurring deep within the Milky Way itself, outflows generated by star formation, or the activity of supermassive black holes at the galactic center might propel gas into the halo, creating HVCs. This phenomenon illustrates the ongoing interactions and exchanges of matter that shape the content and structure of our galaxy. As studies progress, we continue to unravel the complex tapestry of forces that give rise to these intriguing high-velocity clouds in the cosmos. Ultra-diffuse galaxies are a striking class of astronomical objects that challenge conventional wisdom about galaxy formation. These galaxies are characterized by their extraordinarily low surface brightness and large physical size relative to their stellar mass. Instead of a dense concentration of stars, ultra-diffuse galaxies exhibit a diffuse distribution, often making them difficult to detect. Their existence has prompted a re-evaluation of how galaxies can evolve in the universe. One explanation for the formation of ultra-diffuse galaxies involves their origins within larger galaxy clusters. It is believed that these galaxies may form through a process where they strip away gas and stars during interactions with other galaxies in crowded environments. Tidal forces exerted during close encounters may stretch and disrupt these galaxies, leading to a lower density of stars. This scenario suggests that ultra-diffuse galaxies could actually be remnants of larger galaxies that have undergone significant gravitational interactions. Another intriguing hypothesis proposes that ultra-diffuse galaxies could represent a previously unrecognized evolutionary path for galaxy formation. In this view, they might arise from the quick collapse of gas clouds in the early universe without the additional stellar feedback that often accompanies star formation. This rapid process could lead to the formation of a galaxy with a lot of dark matter but relatively fewer stars, resulting in the low surface brightness that defines ultra-diffuse galaxies. Furthermore, the role of dark matter cannot be overlooked. These galaxies could contain substantial amounts of dark matter which helps maintain their structure while giving them the appearance of being less populated with stars. The dynamics of dark matter may allow these galaxies to remain stable despite their low stellar density, creating the unique characteristics that distinguish ultra-diffuse galaxies from more traditional galactic structures. As we continue to explore these fascinating objects, we gain insight into the multitude of pathways through which galaxies can evolve over cosmic time. Fast radio bursts, often referred to as FRBs, are one of the most intriguing phenomena in modern astrophysics. These are brief, intense bursts of radio waves originating from deep space, and they last only for a few milliseconds. Their sudden appearance and powerful emissions pose a significant mystery, capturing the attention of astronomers and researchers worldwide. Although the exact cause of these enigmatic bursts remains uncertain, several theories have been put forward. One possibility is that they originate from rapidly rotating neutron stars known as pulsars. The immense magnetic fields and rotation of pulsars can generate bursts of electromagnetic radiation. Some researchers speculate that certain neutron stars might possess properties that allow them to emit these exceptionally bright radio signals, particularly when interacting with surrounding material. Another hypothesis suggests that fast radio bursts could be connected to the cataclysmic events associated with magnetas, which are a type of neutron star with extremely strong magnetic fields. When these magnetars undergo certain activities, such as starquakes or magnetic field rearrangements, they can emit bursts of high-energy radiation. The idea of magnetar-related bursts has gained traction, especially since some FRBs have been observed to repeat, suggesting a more active and explosive source. Additionally, there is speculation that the phenomenon might be linked to events on a cosmic scale, such as collisions between compact objects or even interactions involving black holes. The myriad of potential explanations underscores the complexity and range of physical processes that could lead to the formation of fast radio bursts. As more observations are gathered and new technologies come online, researchers hope to untangle this cosmic riddle, shedding light on the origins of these brief but powerful signals from the universe. The thick disk of a galaxy is an intriguing component of its structure, lying above and below the central plane of the thin disk, where most of the galaxy's stars are concentrated. This thick disk is characterized by a greater height, a higher density of older stars, and a distinct population of stars that differ in composition and age from those in the thinner disk. Understanding the formation and characteristics of the thick disk is essential for piecing together the history of our galaxy and others. One principal explanation for the origin of the thick disk centers around the processes involved in galaxy formation and evolution. During the early stages of a galaxy's life, interactions with other galaxies, including mergers and accretion of gas, can lead to the dispersion of stars into a thicker structure. These gravitational interactions can perturb stars, causing them to gain sufficient energy to move away from the flat plane of the thin disk, forming what we now recognize as the thick disk. Additionally, internal processes within the Milky Way may contribute to the thick disk's formation. As stars form and evolve, some of them can explode as supernovae, enriching the surrounding environment with heavier elements. The energy released during these explosions may also serve to stir up stars in the thin disk, lending to the creation of a component that we observe as the thick disk. In many cases, the thick disk is populated by older stars that have remained relatively untouched since their formation. This suggests that the thick disk may harbor remnants from the early universe, potentially offering clues to the conditions present at that time. The study of the thick disk continues to be an active area of research that helps astronomers unravel the complex assembly of the Milky Way and provides insights into the evolution of galaxies in the broader universe. Ultra-high-energy cosmic rays are a fascinating aspect of the cosmic landscape, consisting of charged particles that possess energies exceeding 1 billion electron volts. These mysterious particles are believed to originate from powerful astrophysical phenomena. Understanding their sources not only unravels the mysteries of cosmic rays, but also opens a window to the extreme conditions present in the universe. One leading hypothesis suggests that supernova remnants are significant contributors to the ultra-high-energy cosmic rays. When massive stars exhaust their nuclear fuel, they explode in supernova events, releasing an enormous amount of energy. The shock waves produced by these explosions can accelerate particles to extraordinary speeds, generating cosmic rays. As these remnants evolve, they provide a natural environment for the acceleration processes that lead to the creation of ultra-high-energy particles. Another intriguing potential source is active galactic nuclei, which house supermassive black holes at the centers of galaxies, including our own Milky Way. These black holes can power jets of high-energy particles that travel vast distances into space. The extreme conditions surrounding these jets might be responsible for the generation of ultra-high-energy cosmic rays, as particles are accelerated to incredibly high speeds within the intense gravitational and magnetic fields present in those regions. Gamma-ray bursts, one of the most energetic phenomena in the universe, are also considered potential sources of ultra-high-energy cosmic rays. Occurring during the collapse of massive stars or the collision of neutron stars, these bursts release vast amounts of energy over a brief period and can accelerate particles to incredible energies as well. While these candidates shed light on our understanding of cosmic rays, the precise mechanisms behind the creation of ultra-high-energy cosmic rays remain an active area of research. Continued observations and advancements in detection technology will help clarify their origins and enhance our understanding of the dynamic processes taking place in our galaxy and beyond. The discovery of exoplanets, or planets outside our solar system, marked a significant turning point in astronomy and our understanding of planetary systems. Prior to the first confirmed detection of an exoplanet in the mid-1990s, our knowledge was largely limited to the 8 planets orbiting our Sun. The realization that planets could exist around other stars opened up a new frontier in the study of astrophysics, leading to profound implications for our understanding of how planetary systems form and evolve. The methods used to detect exoplanets, such as the transit method and radial velocity technique, have revealed a remarkable diversity of planetary systems in our galaxy. Many of these exoplanets do not resemble the familiar worlds of our solar system. Astronomers have discovered hot Jupiters, massive gas giants that orbit very close to their host stars, as well as Earth-sized rocky planets in the habitable zone where conditions might be suitable for life. This broad diversity challenges existing models of planetary formation, suggesting that the processes leading to the formation of planets are more complex and varied than previously thought. Additionally, the sheer number of exoplanets observed, numbering in the thousands, implies that our solar system is just one of many configurations possible in the universe. This realization has led to new theories about how planetary systems can develop in different environments. For example, the presence of multiple planets in compact orbits around the same star could indicate different mechanisms of formation and migration compared to our own solar system's layout. The exploration of exoplanets has also reignited questions about the possibility of life beyond Earth. By studying the atmospheric composition of certain exoplanets, astronomers can potentially identify biosignatures or conditions conducive to life. This search for extraterrestrial life has implications far beyond science, influencing philosophy, biology, and our understanding of humanity's place in the universe. The discovery of exoplanets continues to drive scientific inquiry and have profound impacts on our understanding of planetary systems, adding to the grand narrative of cosmic exploration. The detection of gravitational waves opened a remarkable new window into our understanding of the universe, allowing astrophysicists to observe cosmic events in a way that was previously unimaginable. Predicted by Albert Einstein over 100 years ago as a consequence of his theory of general relativity, gravitational waves are ripples in space-time produced by some of the most violent and energetic processes in the cosmos, such as colliding black holes or neutron stars. When the first gravitational waves were detected by the LIGO Observatory in 2015, it marked a pivotal moment in astronomy. The observation confirmed the existence of these waves and provided direct evidence for the merging of black holes, offering insights into their properties, such as mass and spin. Prior to this event, black holes were largely inferred from indirect evidence, and the ability to observe them directly through gravitational waves revolutionized our understanding of these enigmatic objects. The implications of gravitational wave detections extend beyond black holes. The merger of neutron stars, another catastrophic event that produces gravitational waves, was observed in 2017. This observation was groundbreaking as it coincided with electromagnetic signals, marking the first instance of a multi-messenger astronomy event. By studying both gravitational waves and light emitted during the merger, scientists gained new insights into the processes involved in heavy element production, such as gold and platinum, as well as the mechanics of neutron-star collisions. Moreover, the study of gravitational waves has the potential to probe the very fabric of space-time itself. It opens pathways to exploring fundamental questions about the universe, including the nature of gravity, the behavior of matter under extreme conditions, and even the possibility of uncovering information from the early universe shortly after the Big Bang. As gravitational wave detection technology continues to improve, it promises to deepen our understanding of cosmic phenomena and unravel some of the universe's most profound mysteries. The mapping of the cosmic microwave background radiation, or CMB, has profoundly enhanced our understanding of the universe and significantly refined cosmological models. The CMB represents the afterglow of the Big Bang, a remnant radiation that fills the universe and provides a snapshot of the cosmos when it was just about 380,000 years old. By studying this ancient light, astronomers can gain insights into the conditions that existed during the early universe. Detailed observations from missions like the Wilkinson Microwave Anisotropy Probe and the Planck satellite have produced incredibly precise maps of the CMB. These maps reveal tiny fluctuations in temperature across the sky, corresponding to density variations in the early universe. These anisotropies serve as a record of the primordial density fluctuations that eventually led to the formation of galaxies and large-scale structures we see today. By analyzing these patterns, scientists can infer critical parameters such as the universe's rate of expansion, its composition, and its overall geometry. The improved measurements of the CMB have corroborated and refined the standard cosmological model known as lambda cold dark matter. According to this model, the universe consists of roughly 70% dark energy, 25% dark matter, and 5% ordinary matter. This framework has provided a comprehensive explanation for a wide range of astronomical observations, making it one of the most successful models in understanding large-scale cosmic evolution. Furthermore, the mapping of the CMB has also prompted new questions and avenues of research. Discrepancies between measurements of the universe's expansion rate, known as the Hubble constant, derived from CMB data and those obtained from local observations have sparked debates and investigations into potential new physics beyond the standard model. As researchers continue to analyze CMB data, they not only refine our current understanding, but also pave the way for breakthroughs that could reshape our cosmological theories and reveal deeper truths about the universe. Multi-messenger astronomy represents a transformative approach to studying the cosmos, combining information from different types of astrophysical signals, including electromagnetic radiation, gravitational waves, neutrinos, and cosmic rays. This field has expanded dramatically in recent years, leading to significant discoveries and a deeper understanding of the universe's most extreme phenomena. One of the most notable achievements in multi-messenger astronomy came with the merger of neutron stars detected in 2017. This event was extraordinary, not only because it was observed in gravitational waves, but also because it was concurrently detected by numerous electromagnetic signals across the spectrum, from gamma rays to optical light. This marked the first time astronomers could correlate gravitational waves with electromagnetic observations, revealing vital information about the nature of neutron star collisions and the processes involved in heavy element production. Researchers learned that events like these are responsible for the creation of elements such as gold and platinum, forging a powerful link between cosmology and nuclear synthesis. Additionally, the simultaneous detection of different messengers has enabled scientists to confirm or challenge existing theories about the origins of cosmic rays. High-energy cosmic rays, composed of charged particles from various sources, have been linked to events like gamma-ray bursts and supernovae. Multi-messenger studies have provided critical evidence for understanding how these ultra-high-energy particles are accelerated and where they originate in the universe. Moreover, the emergence of new observatories dedicated to different types of astrophysical signals has significantly enhanced the breadth of multi-messenger observations. Opportunities to explore areas such as high-energy neutrinos, subatomic particles generated in extreme environments, have opened up fresh perspectives on phenomena like active galactic nuclei or supernovas. These observations are providing fresh insights into the fundamental processes governing the evolution of the universe and the interactions of matter and energy at the highest energies observed. The advancements in multi-messenger astronomy underscore the collaborative nature of modern astrophysics, where varied disciplines converge to unlock the mysteries surrounding violent cosmic events. As researchers continue to refine detection techniques and enhance data-sharing capabilities, the future of multi-messenger astronomy promises even greater revelations about the underlying mechanics of our universe. Deep field observations have significantly transformed our understanding of galaxy formation and evolution, providing a profound look into the distant universe. These observations involve taking long exposure images of tiny regions of the sky, allowing astronomers to capture faint and distant galaxies that would otherwise remain hidden from view. The Hubble Space Telescope's deep field images in particular have unveiled thousands of galaxies, each with its own history, thereby enriching our comprehension of the history of the cosmos. One of the most impactful contributions of deep field observations is the ability to study the universe at various epochs. By examining galaxies at different distances, which correspond to different times in the universe's history, researchers can track how galaxies formed and evolved over billions of years. This has revealed that the majority of galaxy formation occurred when the universe was relatively young, providing critical insight into the processes that drive star formation and the development of galaxy structures. These observations have led to the discovery of many types of galaxies, including those not previously accounted for in theoretical models. For instance, astronomers have identified a wealth of very young and irregular galaxies, illuminating diverse pathways of galaxy formation that challenge the traditional view of a straightforward progression from smaller to larger, well-ordered spirals and ellipticals. This complexity suggests that galaxy formation is influenced by a variety of factors, including mergers, interactions, and environmental conditions, thereby complicating our understanding of how galaxies evolve over time. Moreover, deep-field imaging has significantly enhanced our perception of the role that dark matter plays in galaxy formation. The distribution of galaxies uncovered in these observations has provided evidence for the existence of dark matter, suggesting that it forms the scaffolding on which galaxies build. Understanding the relationship between baryonic matter, like stars and gas, and dark matter is crucial for developing more accurate models to account for the observed structures in the universe. As technology continues to improve and more advanced observatories are launched, deep-field studies will remain vital for unlocking the complexities of galaxy formation. These observations allow astronomers to piece together the intricate puzzle of how galaxies like our own Milky Way came to be, revealing the dynamic history of the universe itself. Recent galactic observations have significantly advanced our understanding of dark matter, a mysterious substance that constitutes about 26% of the universe's total mass energy content. Although dark matter does not emit, absorb, or reflect light, its gravitational effects can be observed in the motion of galaxies, clusters, and even the cosmic web that connects them. These observations have provided important insights into the nature, distribution, and dynamics of dark matter in the universe. One key breakthrough has come from studying the rotation curves of galaxies. As scientists measured the speeds of stars and gas within galaxies, they discovered that these rotation rates remain high even at large distances from the galactic center. According to the laws of gravity, one would expect stars further from the center to rotate more slowly due to the decreasing gravitational influence of visible matter. However, the observed speeds indicated the presence of a substantial amount of unseen mass, dark matter, that shapes the gravitational potential of galaxies. This evidence has led to the development of dark matter halo models, which describe how dark matter is distributed in and around galaxies. Additionally, observations of galaxy clusters have provided crucial insights into the behavior of dark matter on larger scales. By measuring the mass of clusters through gravitational lensing, a phenomenon where light from more distant objects is warped by the gravitational field of the cluster, astronomers have been able to map the distribution of dark matter. These maps reveal that dark matter often forms a halo surrounding visible matter, acting as an invisible framework for the galaxies within clusters. The study of these mass distributions has reinforced the idea that dark matter is essential for holding clusters together and affects their evolution over cosmic time. Furthermore, the discovery of the cosmic web, a vast structure of interconnected filaments formed by dark matter, has expanded our perspective on how dark matter influences the universe. Observations of galaxy redshifts reveal that galaxies are not distributed randomly, but rather follow the patterns laid down by dark matter's gravitational influence. This work has reinforced the concept that dark matter plays a critical role in the large-scale structure of the universe, affecting how galaxies are arranged and how they interact over billions of years. As observational techniques improve and new surveys are conducted, our understanding of dark matter continues to evolve. Future discoveries will likely deepen our insights into this elusive component of the universe and help answer fundamental questions about the nature of gravity, the formation of cosmic structures, and whether dark matter consists of known or exotic particles. Space-based observatories have dramatically transformed our view of the Milky Way, providing astronomers with unprecedented access to data that improve our understanding of our galaxy's structure, dynamics, and composition. Unlike ground-based telescopes, which are affected by Earth's atmosphere, space-based instruments can capture clearer and more detailed observations across a broad range of wavelengths, including visible, infrared, and radio light. One of the most significant advancements has come from the perspective offered by instruments like the Hubble Space Telescope, which has revealed stunning images and insights about individual stars, star clusters, and the formation of new stars within our galaxy. Hubble's ability to peer deep into stellar nurseries has enhanced our understanding of the processes that govern star formation and how these processes vary across different regions of the Milky Way. Coupled with infrared telescopes like the Spitzer Space Telescope, which can penetrate dust clouds that obscure visible light, astronomers are now able to observe the inner workings of the galaxy with remarkable clarity. Moreover, missions such as the European Space Agency's Gaia Observatory have revolutionized our understanding of the Milky Way's structure by providing a comprehensive three-dimensional map of its stars. Gaia's astrometric measurements have allowed scientists to determine the positions, distances, and motions of over 1 billion stars, revealing the galaxy's detailed structure and dynamics. This mapping helps researchers to identify the distribution of stars, stellar clusters, and the overall shape of the Milky Way, enhancing our knowledge of its spiral arms and the distribution of stellar populations, including old stars, young stars, and those with distinct chemical compositions. In addition to mapping stars, space observatories have influenced our understanding of the Milky Way's dark matter content. Observations of stellar motions within the galaxy, coupled with space-based measurements, have provided evidence of a dark matter halo surrounding the Milky Way. These findings allow scientists to study how the galaxy's gravitational pull affects its stars and gas, providing insight into the dynamics of dark matter and its role in the galaxy's formation and evolution. Ultimately, space-based observatories have become vital tools in astronomical research, enabling a more detailed and nuanced picture of the Milky Way. As technology continues to advance, future missions promise to expand our understanding even further, guiding us toward new discoveries regarding our galaxy's history, structure, and place in the wider universe. High redshift galaxy observations have provided invaluable insights into the early universe, allowing astronomers to probe regions that existed when the universe was a fraction of its current age. These galaxies, situated at great distances from us, correspond to epochs where the universe was more dynamic and rapidly evolving, usually considered to be around 2 to 10 billion years after the Big Bang. Observations of these distant galaxies have revealed critical information about the formation, evolution, and properties of early cosmic structures. One significant discovery is that galaxies in the early universe appear more irregular and chaotic compared to their more mature counterparts today. Many high redshift galaxies show signs of active star formation and are often smaller and less structured than contemporary galaxies like our Milky Way. This suggests that the processes driving galaxy formation were different in the early universe, leading to a rapid buildup of stars and gas. The intense star formation rates observed indicate that the cosmos was a hotbed of activity, with galaxies frequently interacting and merging, which contributes to their later development into the larger, more organized structures seen today. Moreover, high redshift observations have illuminated the chemical evolution of the universe. By studying the light emitted by distant galaxies, astronomers can detect the presence of various elements. These observations show that early galaxies contained predominantly hydrogen and helium, with heavier elements forming through stellar processes. The rate at which these metallic elements were produced has provided insights into the life cycle of stars, helping scientists understand how the abundance of heavier elements evolved in the universe over time. The cosmic history of dark matter has also been discerned through these observations. High redshift galaxies allow researchers to study how dark matter halos formed and evolved alongside visible matter. The relationship between dark matter and baryonic matter in early galaxies has been crucial for developing cosmological models, shedding light on how gravity influenced the structures that would later become the backbone of the modern universe. As researchers use more advanced telescopes and methods to observe high redshift galaxies, such as the James Webb Space Telescope, we expect to deepen our understanding of the processes that shaped the universe's infancy. These continued observations promise to reveal even more about the origins and evolution of galaxies, aiding in the quest to understand our cosmic history and the fundamental forces at play in the universe. The discovery of interstellar objects like Oumuamua has significantly shifted our perspective on our solar system and the broader dynamics of our galaxy. Oumuamua, which passed through our solar system in 2017, was the first known object not gravitationally bound to our Sun, originating from another star system. This remarkable find opened a new chapter in astronomy, revealing that our solar neighborhood is not an isolated entity, but a dynamic environment teeming with potential visitors from distant star systems. One of the primary implications of Oumuamua's discovery is the realization that interstellar objects could be more common than previously thought. This awareness has led astronomers to reconsider how we understand the distribution of material in the galaxy. Previously, most of our knowledge about celestial objects was derived from those within the solar system. The existence of interstellar objects suggests that material ejected from other systems, not only stars, but also potentially habitable planets, might traverse interstellar space and eventually encounter our solar system. The peculiar characteristics of Oumuamua have also prompted debates and discussions among scientists about the nature of such objects. Unlike typical comets or asteroids, Oumuamua exhibited an unusual shape, elongated and cigar-like, and showed no detectable cometary activity, which raised questions about its composition and origin. These features have led to various hypotheses regarding its formation, suggesting it may be either a fragment of a larger body or an object shaped by extreme processes in a foreign solar system. Such discussions have spurred a broader investigation into the potential diversity of interstellar objects that could exist and the physical processes that shape them. Furthermore, the study of interstellar objects has implications for astrobiology. Understanding the materials and conditions of other star systems can provide valuable information about the potential for life beyond our solar system. Some researchers speculate that interstellar objects might carry organic compounds or other ingredients necessary for life, which could have been delivered to planets during their formation or evolution. This prospect encourages scientists to explore how life might arise in different environments and contributes to the ongoing search for extraterrestrial life. The excitement generated by Oumuamua has initiated plans to search for and study additional interstellar visitors more actively. Future telescopes and missions will likely enhance our ability to detect and analyze these intriguing objects, ultimately expanding our understanding of the solar system and the myriad of cosmic interactions that shape the universe around us. Recent studies of the stellar populations in the galactic bulge have provided profound insights into the formation and evolution of the Milky Way. The galactic bulge, a densely populated region at the center of our galaxy, contains a rich variety of stars, including many old and metal-rich populations, which hold clues about the history and dynamics of the Milky Way. One significant discovery is the diversity of stellar populations within the bulge itself. Observations have revealed that the bulge is not uniformly composed of old stars, as was once thought. Instead, it includes a mix of stars of different ages and metallicities. This diversity suggests that the bulge formed over an extended period of time, with different episodes of star formation contributing to its current structure. The presence of younger stars alongside older populations indicates that star formation was more active in the bulge than previously assumed, possibly influenced by interactions with surrounding gas and the dynamics of nearby galactic structures. Additionally, studies utilizing advanced spectroscopic techniques have highlighted the importance of understanding the chemical composition of stars in the bulge. By analyzing the abundance of elements, astronomers have been able to trace the process of chemical enrichment in these stellar populations. The range of metallicities observed indicates that some stars formed from gas enriched by earlier generations of stars, thus providing a timeline for the evolution of the bulge. This information aligns with models of growth involving both the early collapse of gas and subsequent accretion of material from the surrounding environment. Furthermore, kinematic studies of bulge stars have revealed significant insights into the dynamics and structure of the bulge. The movement of stars within this central region displays multiple components, including a classical spheroid and a more dynamic bar structure. This complexity indicates that the bulge has experienced significant gravitational interactions and migrations of stars, profoundly influencing its current configuration. Understanding these motions helps researchers piece together the evolutionary history of the Milky Way and the role that the bulge played in shaping the galaxy as a whole. As astronomers continue to utilize advanced telescopes and techniques to study the stars in the galactic bulge, our understanding of this vital region will only deepen. The ongoing investigation into the origins, chemical makeup, and dynamics of bulge populations sets the stage for a more comprehensive view of the Milky Way's history and the processes that drive galaxy evolution over cosmic time. The James Webb Space Telescope, launched in December 2021, represents a significant advancement in our ability to study the Milky Way and its myriad structures. With its cutting-edge instruments and capabilities, Webb is poised to provide unprecedented insights into the galaxy, particularly in areas that have been challenging to explore with previous telescopes. One of the key enhancements Webb brings to the study of the Milky Way is its ability to observe in the infrared spectrum. Many regions of the galaxy, especially star-forming areas, are obscured by dust that blocks visible light. Webb's infrared capabilities will allow astronomers to penetrate this dust, revealing the details of stellar nurseries where new stars and planetary systems are forming. This capability will enhance our understanding of the mechanisms driving star formation and the conditions required for the birth of stars. In addition to studying star formation, the James Webb Space Telescope will facilitate the investigation of the galaxy's structure and dynamics. By conducting detailed surveys of the galactic bulge, disk, and halo, astronomers will gain insights into the distribution of stars, gas, and dark matter. Observations of star clusters and individual star populations will allow for the study of their ages, chemical compositions, and motions, contributing to a clearer picture of the Milky Way's formation history and the processes that have shaped it over billions of years. Webb will also play a crucial role in studying exoplanets within the Milky Way, particularly those in the habitable zones of their stars. Its advanced spectrographs will allow for the analysis of exoplanetary atmospheres by observing the light passing through their atmospheres during transits. This capability will enable scientists to search for potential biosignatures, thereby enhancing our understanding of the conditions that might support life elsewhere in our galaxy. Moreover, the ability to conduct deep-field observations with Webb will allow for the identification of distant, faint objects, including those that may represent the early stages of galaxy formation. Observing these distant galaxies and their formation in relation to the Milky Way will help astronomers explore the evolution of galaxies across cosmic time. Overall, the James Webb Space Telescope promises to transform our study of the Milky Way by providing clearer, more detailed views of its structure, evolution, and the processes occurring within it. As it begins to collect data, Webb will open new avenues of research, deepening our understanding of our galaxy and its place in the broader universe. Adaptive optics represents a significant leap forward in ground-based astronomical observations, addressing one of the primary challenges posed by Earth's turbulent atmosphere. Traditional telescopes face limitations due to atmospheric distortion, which can blur and degrade images of celestial objects. Recent advancements in adaptive optics technology are enhancing our ability to study the Milky Way and other galaxies from the ground with unprecedented clarity and precision. One of the key advancements in adaptive optics is the development of more sophisticated wavefront sensors and correcting algorithms. These systems can swiftly measure the distortion in incoming light caused by atmospheric turbulence and adjust the telescope's optics in real time. By using advanced algorithms and artificial intelligence, astronomers can optimize these corrections, enabling telescopes to produce sharper and more detailed images of stars, nebulae, and other features within our galaxy. Enhanced correction capabilities improve both spatial resolution and contrast, allowing for finer details to be resolved. Another important development is the integration of multiple adaptive optics systems onto a single telescope. This approach, often termed multi-conjugate adaptive optics, involves using multiple deformable mirrors at different locations within the optical path. This configuration allows for corrections over a wider field of view, enabling astronomers to study larger regions of the Milky Way simultaneously while still benefiting from the enhanced image quality. This capability is particularly beneficial for mapping structured features like star clusters and extended nebulae. The advent of high-order adaptive optics represents another advancement, allowing telescopes to correct for more complex distortions caused by the atmosphere. Traditional systems typically corrected for a limited number of modes, but high-order systems can account for a greater variety of distortions, leading to sharper images even in turbulent conditions. This is especially useful when observing closer astronomical phenomena, such as the dynamics of stars in the central bulge of the Milky Way. Moreover, the development of laser guide stars has expanded the utility of adaptive optics. By projecting a laser beam into the atmosphere, astronomers create an artificial star that mimics the behavior of a natural star. This allows for more accurate wavefront corrections in regions where natural guide stars may not be present, improving observations across certain areas of the sky. Laser guide stars can be particularly valuable when studying densely populated regions of the Milky Way, like star clusters and the galactic core. As these advancements in adaptive optics continue to evolve, they hold the potential to revolutionize ground-based observations of the Milky Way and beyond. Improved image quality will enhance our ability to investigate the dynamics and composition of stars, gas, and dust, ultimately leading to groundbreaking discoveries about the structure and history of our galaxy. Gravitational lensing is a powerful and fascinating phenomenon that can be harnessed to study distant parts of the galaxy in ways that would otherwise be impossible. This occurs when a massive object, such as a galaxy or galaxy cluster, exerts a strong gravitational pull that bends the light from more distant objects behind it. This bending of light can amplify and distort the images of those background objects, allowing astronomers to gather valuable information about both the foreground lensing object and the distant sources of light. One of the primary applications of gravitational lensing in the study of distant parts of the galaxy is the magnification of faint objects. When a massive galaxy or cluster acts as a lens, it can enhance the brightness and resolution of more distant galaxies that would be too faint to detect otherwise. This amplification allows astronomers to observe objects situated much further back in the universe, providing insights into their structures, star formation rates, and chemical compositions. By analyzing the light coming from these lensed galaxies, researchers can reconstruct information about their environment and evolutionary history. Gravitational lensing also serves as a tool for mapping the distribution of dark matter. When light from distant galaxies is lensed, the amount of distortion can be connected to the mass of the lensing object. By studying these lensing effects, astronomers can create mass maps of the lensing galaxy or cluster, revealing where dark matter is concentrated. This mapping provides crucial insights into the role that dark matter plays in galaxy formation and evolution, helping to refine our understanding of the cosmos on both large and small scales. Moreover, gravitational lensing can aid in the study of cosmic expansion and the large-scale structure of the universe. By observing how the lensing affects multiple background objects at varying distances, astronomers can infer properties about the expansion rate of the universe and the overall distribution of matter. This information plays a vital role in cosmology, as it helps to address fundamental questions about the universe's composition, growth, and fate. Additionally, Time delays caused by gravitational lensing can be leveraged to study the distances to lensed objects. When light from a background quasar is lensed by a foreground galaxy, the path light takes can vary. This results in differences in the time it takes for the light to reach us. By measuring these time delays, astronomers can gain insights into the geometry of the universe and refine their measurements of cosmological parameters. As we continue to observe more distant parts of the galaxy and beyond utilizing gravitational lensing, we deepen our understanding of not only the sources being lensed, but also the structures and dynamics of the lensing galaxies themselves. The potential applications of gravitational lensing extend the reach of observational astronomy, providing a unique window into the universe's history, composition, and fundamental workings. Artificial intelligence is poised to play a transformative role in analyzing the vast amounts of data generated by modern astronomical observations. As telescopes and space missions continue to produce unprecedented volumes of data, the challenge of efficiently processing and interpreting this information has become increasingly significant. AI and machine learning techniques are emerging as powerful tools to address these challenges, enabling researchers to unlock insights that would otherwise remain hidden. One of the primary applications of artificial intelligence in astronomy is in the classification of astronomical objects. With surveys that catalog millions of stars, galaxies, and other celestial bodies, traditional methods of data analysis can be slow and labor-intensive. Machine learning algorithms can be trained to recognize patterns in data, allowing them to categorize and identify objects rapidly and accurately. This capability is particularly useful in large surveys like those conducted by the Sloan Digital Sky Survey or the upcoming Vera C. Rubin Observatory's Legacy Survey of Space and Time, where identifying different types of astronomical phenomena is essential for further analysis. In addition to classification, AI can also facilitate the extraction of meaningful features from the data that may not be readily apparent. Algorithms can analyze complex datasets, discovering relationships and trends that could help scientists understand cosmic processes. For instance, neural networks have been successfully employed to identify gravitational waves, detect exoplanets, and even uncover subtle signatures in the cosmic microwave background radiation. The ability to process and extract information efficiently enhances our understanding of the universe while reducing the time required for analysis. Artificial intelligence also aids in anomaly detection, identifying unusual or unexpected events in astronomical datasets. As astrophysical phenomena can be rare and sometimes transient, AI systems can flag these outliers for further investigation. Swift identification of supernovae, gamma-ray bursts, or other transient events allows for timely follow-up observations with other instruments, leading to richer datasets and a more comprehensive understanding of such occurrences. Finally, AI can assist in simulating and modeling celestial phenomena. By creating sophisticated models based on existing data, AI can make predictions and generate synthetic datasets that can be compared against observations. This capability not only aids in understanding the underlying physics of astronomical objects, but also helps refine theories related to galaxy formation, star evolution, and other cosmic processes. As the field of astronomy continues to evolve, the integration of artificial intelligence will enhance our capabilities to tackle complex problems, analyze vast quantities of data, and unlock new realms of understanding. The potential for AI to transform how we study the universe is vast, making it a critical ally for astronomers as they continue their quest to unveil the mysteries of the cosmos. Future missions to the outer reaches of the solar system, often referred to as the solar system's edge or edges of the heliosphere, hold substantial promise for improving our understanding of galactic models. The regions beyond Neptune, including the Kuiper Belt and the Oort cloud, represent areas that remain relatively unexplored and hold vital clues about the formation and evolution of our solar system, as well as the environment in which it resides. One key area where such missions can contribute is in the study of trans-Neptunian objects and their characteristics. By sending spacecraft to these distant regions, scientists can gather detailed data on the composition, size, and orbital dynamics of various objects. This information is crucial for understanding the initial conditions that shaped the solar system. For instance, investigating the ratios of different elements and isotopes can provide insights into the processes that influenced early solar system formation and the role of various components in the development of planetesimals, small celestial bodies that could amalgamate to form larger planets. Moreover, missions to the solar system's edge can enhance our understanding of the solar wind and its interactions with the interstellar medium. Understanding how the solar wind interacts with the surrounding galactic environment is vital for refining models of how our solar system exists within the broader structure of the Milky Way. By measuring cosmic rays and the magnetic field in the heliosphere, scientists can gain insights into the processes that govern the movement and evolution of matter throughout the galaxy, which may play critical roles in shaping the galactic environment over time. Another potential contribution is the study of the dynamics of ices and volatiles present in the outer solar system. Observations of icy bodies such as comets and Kuiper belt objects can shed light on the conditions prevailing in the protoplanetary disk that formed the solar system. Understanding these bodies helps to put constraints on the dynamical processes that transported materials from the outer regions of the disk to the inner solar system, influencing the habitability of Earth and potentially other worlds. Finally, the insights gained from missions to the solar system's edge can contribute to enhancing our computational models of galaxy formation and evolution. By combining data from these missions with other astronomical observations, researchers can refine simulations that incorporate factors like the distribution and interaction of matter within galaxy structures. This holistic approach enhances our ability to model how galaxies form, evolve, and interact over cosmic time. As new missions are planned and developed for the outer solar system, they open up exciting possibilities for further investigating the solar system's boundaries. The knowledge gained from these expeditions will not only enrich our understanding of our own cosmic neighborhood, but also contribute to the broader narrative of galactic evolution, ultimately offering deeper insights into our place within the Milky Way. The search for exoplanets has seen a surge in innovation, with a variety of new technologies being developed to detect and characterize these distant worlds. These advancements enhance our ability to discover new exoplanets and gather essential information about their atmospheres, compositions, and potential for habitability. One of the most promising technologies is the use of space-based observatories equipped with advanced photometric capabilities. The James Webb Space Telescope, set to revolutionize exoplanet studies, utilizes highly sensitive infrared instruments that can detect the faint light from exoplanets and analyze their atmospheres. This telescope will employ the transit method to observe the dimming of a star's light as an exoplanet passes in front of it, allowing scientists to measure the size of the exoplanet. Moreover, by conducting spectroscopic observations, Webb will be able to identify specific atmospheric constituents, such as water vapor, methane, and carbon dioxide, providing insights into the planet's composition and potential habitability. Another critical advancement comes from using ground-based telescopes equipped with adaptive optics systems. These systems correct for the distortion caused by Earth's atmosphere, enabling astronomers to directly image exoplanets that are much closer in proximity to their host stars. Using advanced techniques, researchers can minimize the glare from stars and gain better visibility of nearby planets, offering a more direct method of studying their properties. Radial velocity methods have also seen improvements. This technique involves measuring the tiny shifts in a star's spectral lines caused by the gravitational pull of orbiting exoplanets. New instruments such as the espresso spectrograph on the Very Large Telescope in Chile enhance our ability to detect smaller and less massive planets by improving the precision of these measurements. These advancements are instrumental in identifying Earth-like planets in the habitable zone of their stars. Furthermore, The development of machine learning algorithms plays a vital role in processing vast amounts of data generated by exoplanet surveys. These algorithms can sift through light curves from telescopes to identify potential transits of exoplanets more efficiently, helping to distinguish genuine signals from noise. As the amount of data continues to grow, machine learning will be essential for streamlining the identification process and refining our understanding of exoplanet populations. Collaborative projects like the Transiting Exoplanet Survey satellite are also reshaping the search for new worlds. TESS is designed to survey large portions of the sky and identify candidates for further study, laying the groundwork for subsequent observations with other powerful telescopes. As these new technologies are refined and integrated into exoplanet research, they will vastly expand our ability to discover and characterize distant worlds. Insights gained from these advancements will deepen our understanding of planetary formation and evolution and contribute to the ongoing quest to identify potentially habitable planets beyond our solar system. Neutrino astronomy is an emerging field that holds great promise for enhancing our understanding of galactic phenomena. Neutrinos are nearly massless subatomic particles that interact only very weakly with matter, allowing them to travel vast distances through the universe without being significantly impeded or absorbed. This unique property makes neutrinos a powerful tool for probing cosmic events, particularly those occurring in or around our galaxy. One of the primary applications of neutrino astronomy in the study of galactic phenomena is in the observation of high-energy events, such as supernovae. When a massive star undergoes a supernova explosion, a significant portion of its energy is released in the form of neutrinos, which can escape the star nearly unimpeded. Detecting these neutrinos offers a unique insight into the processes occurring during the explosion and the dynamics of the progenitor star. Observations of neutrinos from supernovae can help refine models of stellar evolution and improve our understanding of the mechanisms behind these cataclysmic events. Neutrinos can also provide information about cosmic rays and their origins. Many high-energy cosmic rays are believed to originate from extreme environments, such as supernova remnants, active galactic nuclei, or gamma-ray bursts. When cosmic rays interact with surrounding matter, they can produce neutrinos. By studying the neutrino flux associated with these high-energy events, astronomers can gain insights into the acceleration mechanisms and environments responsible for cosmic ray production. Understanding the link between cosmic rays and neutrinos enhances our overall knowledge of high-energy astrophysical processes within the galaxy. Additionally, neutrino detectors can be used to study the dynamics surrounding black holes. Neutrinos generated in the vicinity of black holes, particularly from accretion disks or jets of material, can reveal information about their environments that is otherwise challenging to observe. By identifying and characterizing the neutrinos associated with these phenomena, researchers can glean insights into the processes associated with material falling into black holes or being ejected in powerful jets. Furthermore, the study of neutrinos can complement observations from other astronomical messengers, like electromagnetic radiation and gravitational waves. This multi-messenger approach enables a more comprehensive understanding of complex astrophysical processes. For instance, simultaneous observations of energetic neutrinos, electromagnetic signals, and gravitational waves from an event can provide a richer picture of the underlying phenomena. As detectors continue to improve in sensitivity and reach, the potential for neutrino astronomy to illuminate galactic phenomena will only grow. Future neutrino observatories, such as the IceCube Neutrino Observatory and others planned for different environments, will expand our ability to observe and study these elusive particles. This growing field has the potential to deepen our understanding of the galaxy and the fundamental processes that shape it, contributing valuable pieces to the complex puzzle of the universe. Advancements in radio astronomy are significantly enhancing our ability to map the structure of the Milky Way, providing crucial insights into the galaxy's formation, dynamics, and overall architecture. Several key developments in technology and methodology are facilitating more detailed and precise observations of our galaxy through radio wavelengths, which can penetrate dust clouds that often obscure other forms of electromagnetic radiation. One of the most notable advancements is the deployment of large radio telescope arrays, such as the Square Kilometre Array and the Very Large Array. These facilities use multiple antennas to collect data that can be combined to create high-resolution images of radio emissions from various sources within the Milky Way. By increasing the collecting area and improving sensitivity, these arrays enhance the ability to observe faint signals from distant regions of the galaxy, helping to map the distribution of neutral hydrogen, molecular clouds, and other important constituents. Another significant development is the use of radio interferometry, a technique that combines signals from separate radio dishes to simulate the performance of a much larger telescope. This method has substantially improved spatial resolution, allowing astronomers to discern finer details in the structures they study. For instance, radio interferometry is particularly effective in mapping the distribution and kinematics of gas and stars in different regions of the Milky Way, from the galactic center to the outskirts. The application of advanced algorithms and machine learning techniques is also revolutionizing radio astronomy. These computational tools can be employed to process vast amounts of data generated by radio observations, helping to identify and classify various celestial objects and phenomena more efficiently. By automating the analysis of large datasets, astronomers can more rapidly uncover new information about the Milky Way's structure, such as the distribution of stellar populations, star formation regions, and the influence of dark matter. Additionally, the integration of simultaneous multi-frequency observations is paving the way for more comprehensive studies of the Milky Way's structure. By utilizing different radio wavelengths, astronomers can probe various components of the galaxy. For instance, observing hydrogen gas at 21 centimeters allows for the mapping of neutral hydrogen, while observations of different molecular lines, such as carbon monoxide, can provide insights into the distribution of molecular clouds essential for star formation. Lastly, the advancement of pulsar timing techniques, which involve monitoring the regular signals emitted by pulsars, is proving invaluable for studying the overall structure of the Milky Way. These measurements help to measure the curvature of space and the effects of gravity, contributing to our understanding of the galaxy's dynamics and expansion. As these advancements in radio astronomy continue to develop, our ability to map and understand the Milky Way's structure will significantly improve. The detailed insights gained from these observations will deepen our understanding of the galaxy's history, evolution, and the complex processes that shape its vast and intricate architecture. Space-based interferometry offers a groundbreaking approach to studying galactic dynamics by providing high-resolution observations of celestial objects and phenomena. This technique involves combining signals from multiple telescopes or detectors, effectively simulating a much larger aperture to achieve greater sensitivity and resolution than traditional single-telescope observations. The benefits of space-based interferometry are particularly significant for understanding various aspects of how galaxies, including our own Milky Way, function and evolve. One of the primary advantages of space-based interferometry is its ability to overcome the limitations imposed by Earth's atmosphere. Ground-based telescopes often experience distortions in their observations due to atmospheric turbulence, which can blur and degrade image quality. Space-based interferometers operate outside of the atmosphere, allowing for much clearer and sharper imaging of distant galaxies. This enhanced clarity enables astronomers to observe fine details in the movements and structures of stars and gas within galaxies, providing invaluable data for modeling their dynamics. By utilizing high-resolution observations from space, interferometry can significantly improve measurements of stellar motions within galaxies. Understanding how stars move under the influence of gravity enables astronomers to unravel the complex gravitational interactions that govern galaxy dynamics. For instance, detailed observations can help determine the mass distribution within galaxies, shedding light on the role of dark matter and its influence on the orbital dynamics of visible matter. These insights contribute to refining our models of galaxy formation and evolution. Additionally, space-based interferometry can facilitate the study of various galactic features, such as spiral arms, bars, and density waves. By providing precise measurements of their structure and dynamics, researchers can gather information about how these features evolve over time and their impact on star formation processes. Understanding the interplay of these components is crucial for unveiling the mechanisms that shape the overall architecture of galaxies. The capability to observe active galactic nuclei and their associated jets with space-based interferometers also expands our understanding of galaxy dynamics. Interferometry allows astronomers to resolve the complex interactions occurring near supermassive black holes, studying how they influence their host galaxies and the surrounding cosmic environment. These observations can reveal how energy and matter are transferred and distributed, leading to insights about the coevolution of galaxies and their central black holes. Furthermore, the capability to conduct precise observations of galaxies at various distances through space-based interferometry enables a comparative approach to studying galaxy dynamics. This approach can uncover how the dynamics of galaxies may differ across cosmic time, revealing evolutionary patterns and the overall influence of the universe's expansion on galactic behavior. As advancements in space-based interferometry continue, they promise to enhance our understanding of galactic dynamics significantly. By providing detailed and high-resolution data, this technique will deepen our comprehension of the complex interplay of forces that govern galaxy formation and evolution, and allow us to build more accurate models of the universe's structure and development. Quantum computing holds remarkable potential for simulating complex galactic systems, offering capabilities that could significantly advance our understanding of the universe. Traditional computers rely on binary processing, which can become inefficient when tasked with modeling the intricate interactions and vast scales involved in astrophysical phenomena. Quantum computing, on the other hand, leverages the principles of quantum mechanics, using qubits to represent and process information in ways that classical computers cannot match. One of the significant advantages of quantum computing lies in its ability to handle complex calculations involving many-body interactions, which are common in astronomical simulations. For instance, simulating the gravitational interactions among thousands or millions of stars in a galaxy can be computationally intensive and time-consuming on classical computers. Quantum computers can potentially perform these calculations more efficiently, allowing for detailed modeling of stellar dynamics, mergers, and galactic interactions in a fraction of the time currently required. Additionally, quantum computing can enhance simulations of molecular dynamics, which is critical for understanding star formation and the behavior of interstellar gas and dust. The processes that govern the formation of stars from molecular clouds involve intricate interactions between particles at quantum levels. Quantum computers can model these interactions more accurately, providing insights into how stars form, evolve, and influence their environments. This capability can lead to a better understanding of the life cycles of stars and their contributions to the chemical evolution of the galaxy. Furthermore, quantum computing can improve the analysis of large datasets generated by astronomical surveys. The complexity and volume of data from observatories and simulations can be overwhelming, making it difficult to extract meaningful insights. Quantum algorithms designed for optimization and machine learning tasks could enhance data processing, enabling faster and more comprehensive analysis of galactic phenomena. This could facilitate the identification of patterns, trends, and anomalies within the data, leading to new discoveries about the structures and dynamics of galaxies. Quantum simulations may also provide deeper insights into dark matter and dark energy, two components that play significant roles in shaping the universe's structure and expansion. By accurately modeling the effects of dark matter on galaxies and galaxy clusters, researchers can better understand its distribution and behavior. This understanding is critical for refining our cosmological models and exploring the fundamental nature of these mysterious components. Chi. While quantum computing is still in its early stages, ongoing advancements in quantum hardware and algorithms are paving the way for its application in astrophysics. As scientists develop more robust quantum systems, the potential to simulate and understand complex galactic systems will expand, contributing to a deeper comprehension of the universe's formation, evolution, and underlying physical laws. The integration of quantum computing into astronomical research may ultimately revolutionize our approach to studying the cosmos, providing tools to tackle questions that were previously considered intractable. The Milky Way is not just a solitary entity in the cosmos. It is part of a vast and intricate web of structures that make up the universe. Understanding its place within this larger structure involves examining various scales, from local groupings to the expansive cosmic web that connects galaxies across great distances. At the most immediate scale, the Milky Way belongs to a group of galaxies known as the Local Group, which includes over 50 galaxies, with the Andromeda Galaxy being the largest and closest major neighbor. The gravitational interactions among these galaxies influence their shapes, motions, and star formation processes. Within the Local Group, the Milky Way and Andromeda are the two dominant galaxies, and they are expected to eventually collide and merge, reshaping both galaxies significantly over billions of years. Extending beyond the Local Group, the Milky Way is part of the larger Laniakea supercluster, a massive collection of galaxy groups and clusters. This supercluster spans over 500 million light-years and contains approximately 100,000 galaxies. The gravitational pull of the Milky Way, along with that of its neighbors, plays a role in the dynamics of this supercluster. Understanding how the Milky Way interacts with other galaxies within Laniakea provides vital insights into the gravitational relationships and cosmic flows that define large-scale structures in the universe. On an even grander scale, the universe is structured as a complex cosmic web, consisting of filaments and voids created by the distribution of dark matter. Galaxies, including the Milky Way, tend to inhabit these filamentary structures where matter has coalesced, while vast voids contain fewer galaxies. The position of the Milky Way within this cosmic web influences its interactions with other galaxies and the distribution of matter in its vicinity. Observing the large-scale structure of the universe reveals patterns that help researchers understand how galaxies formed and evolved over cosmic time. Moreover, the Milky Way's motion should be considered on a cosmic scale. It is moving toward the Andromeda Galaxy and the Centaurus A galaxy, as well as in the direction of the Great Attractor, a region of gravitational influence within the Laniakea supercluster. This motion contributes to our understanding of cosmic dynamics, showing how local structures are influenced by larger forces within the universe. Overall, the Milky Way's position and interactions within these various hierarchical structures contribute to our broader understanding of the universe's evolution. The dynamical processes governing the Milky Way's formation, including its acquisition of gas and the merger with smaller galaxies, provide valuable context for studying other galaxies. By placing our galaxy within the large-scale tapestry of the cosmos, we can better appreciate the intricacies of galactic formation, evolution, and the complex relationships that define the universe as a whole. The Milky Way serves as a critical laboratory for understanding the evolution of the cosmos, offering insights into the processes that have shaped galaxies and the universe over billions of years. By studying our galaxy's formation, structure, and dynamics, scientists glean valuable information about broader cosmic phenomena and the history of the universe itself. One significant aspect is the Milky Way's formation history. Our galaxy formed through a series of complex processes that began shortly after the Big Bang, involving the collapse of gas and dark matter to create stars and other structures. By examining the Milky Way's stellar populations and their age distributions, researchers can piece together a timeline of stellar evolution that aligns with models of cosmic evolution. The presence of ancient stars, particularly in the galactic halo and bulge, provides evidence of the early universe and the conditions that prevailed during the first generations of star formation. The Milky Way also sheds light on the role of interactions and mergers in galaxy evolution. Its history is marked by numerous mergers with smaller dwarf galaxies, which contributed to its growth and chemical enrichment. By studying these interactions, astronomers can understand how galaxies accumulate mass and evolve over time. These processes reflect similar dynamics observed in other galaxies and provide insights into the statistical processes of galaxy formation across the universe. Moreover, the Milky Way's spiral structure serves as a paradigm for understanding the dynamics of barred and spiral galaxies. Observations of its gas dynamics, star formation rates, and the influence of dark matter reveal how gravitational forces shape galactic structures. By examining how the Milky Way regulates star formation and manages the distribution of matter, researchers can draw parallels to other spirals and infer the underlying mechanisms that govern galaxy formation more generally. The study of the Milky Way's chemical composition also offers essential clues about cosmic evolution. Elements heavier than hydrogen and helium were formed in stellar interiors and dispersed into the interstellar medium through supernova and stellar winds. By analyzing the metallicity of stars in various regions of the Milky Way, astronomers can track the history of element formation and understand the processes that led to the distribution of matter throughout the galaxy, contributing to models of chemical enrichment across the universe. Additionally, the Milky Way's interaction with its environment, including its place within the local group and the Laniakea supercluster, provides insights into the structures of the universe. Understanding how galaxies behave in clusters and superclusters helps refine our knowledge of cosmic evolution, including the distribution of dark matter, the effects of cosmic expansion, and the behavior of different galaxy types. As ongoing observations and advancements in technology provide more detailed data about the Milky Way, our understanding of its role in cosmic evolution will continue to deepen. The lessons learned from our galaxy will help inform theories about the vast array of galaxies observed across the universe, enhancing our comprehension of the intricate relationships and processes that govern cosmic evolution over time. The chemical composition of the Milky Way galaxy serves as a rich archive of cosmic history, reflecting the processes and events that have shaped the universe since the Big Bang. This chemical makeup provides insights into stellar evolution, nuclear synthesis, and the dynamic cycles of matter that occur throughout the galaxy and beyond. Initially, the universe was composed mostly of hydrogen and helium, the lightest elements formed during the Big Bang nucleosynthesis. Over time, stars began to form from this primordial gas. Through the life cycles of stars, heavier elements, often referred to as metals in astronomical contexts, were produced via nuclear fusion processes. More massive stars, after exhausting their nuclear fuel, exploded as supernovae, ejecting these heavier elements back into the interstellar medium. This enrichment of the galactic gas occurs over millions to billions of years, creating a cycle where new stars are born from material that has been altered by previous generations of stars. Studying the chemical composition of stars throughout the Milky Way enables astronomers to unravel the history of this enrichment process. For example, ancient stars in the halo and bulge of the galaxy often exhibit lower metallicities, indicating they formed early in the galaxy's life when fewer heavy elements were available. By examining these older stars, researchers can infer the conditions present in the early universe and the timescales over which stars produced and distributed heavier elements. Conversely, stars formed in regions with higher metallicity typically resulted from gas that had already been enriched by previous stellar generations. The distribution of metallicity across the galaxy, from the core to the outer regions, sheds light on the processes of gas inflow and outflow, star formation rates, and the influence of galactic dynamics. The variation in metallicity provides clues about how interstellar gas recycled throughout the galaxy, contributing to the formation of planets and other celestial objects. Furthermore, the study of specific elements and their ratios provides insights into different stellar processes. For example, certain elements such as carbon and oxygen are primarily produced in the interiors of medium-mass stars and released during their later stages as red giants. In contrast, supernovae primarily produce elements like iron and nickel. By analyzing the abundance of these elements in various stellar populations, astronomers can trace the history of star formation and the types of supernova that have occurred within the galaxy. Additionally, the Milky Way's chemical composition is closely tied to its interactions with surrounding galaxies and the intergalactic medium. For instance, processes such as mergers and accretion can introduce new gas and elements into the galaxy, shaping its chemical evolution. By examining the behavior of gas flows and how they influence the galaxy's enrichment, researchers can further understand the interconnectedness of galaxies and the universe. The chemical composition of the Milky Way provides a detailed record of the galaxy's history and evolution, reflecting the complex processes that have occurred since the universe's inception. By studying this composition, scientists gain essential insights into stellar evolution, nucleosynthesis, and the dynamic cycles of matter that characterize the ongoing story of the cosmos. The Milky Way galaxy plays a crucial role in testing cosmological models due to its relatively close proximity and well-studied structure. Its characteristics allow astronomers to examine and validate theories about galaxy formation, evolution, and the underlying physics governing the universe. By analyzing the Milky Way's properties, scientists can evaluate how effectively these models predict galactic behaviors and interactions. One of the primary areas where the Milky Way is instrumental is in the study of dark matter. Cosmological models suggest that dark matter makes up a significant portion of the universe's total mass, influencing both large-scale structures and individual galaxies. By investigating the rotation curve of the Milky Way, how the speed of stars changes with distance from the center, astronomers can infer the presence and distribution of dark matter. These observations help confirm or challenge predictions made by cosmological models regarding dark matter's role in shaping galaxy dynamics, structure, and formation. The Milky Way also serves as a benchmark for understanding galaxy formation and evolution in the broader context of the universe. Theories suggest that galaxies develop through processes of mergers and interactions with smaller galaxies, which contribute to growth over time. By studying the Milky Way's history and its interactions with satellite galaxies, such as the large and small Magellanic Clouds, researchers can test models of hierarchical structure formation. Observations can reveal patterns aligning with predictions about galaxy mergers, interactions, and how they contribute to changes in a galaxy's morphology and star formation rates. Moreover, the Milky Way's chemical composition reflects the processes of nucleosynthesis and chemical enrichment across cosmic history. By examining the abundance of various elements in different stellar populations, astronomers can assess the accuracy of models describing the evolution of matter in the universe. This chemical history provides a basis for understanding how galaxies formed and evolved in the context of cosmic timescales. Another critical aspect is the Milky Way's role as an observational anchor for cosmological measurements, such as the Hubble constant, which describes the universe's expansion rate. By measuring distances to objects within the Milky Way and employing methods such as parallax, researchers can establish fundamental benchmarks that inform larger-scale measurements. The accuracy of the Hubble constant derived from local observations can then be compared with values obtained from observations of distant galaxies, helping to test the consistency of cosmological models. Lastly, the study of our galaxy in the context of the cosmic web contributes to understanding how galaxies interact and evolve on a larger scale. By observing the Milky Way's surroundings, including local and neighboring groups of galaxies, scientists can explore how the Milky Way fits into the broader structures of filaments and voids predicted by cosmological models. In conclusion, the Milky Way serves as a critical point of reference for testing various aspects of cosmological models. Its detailed study allows researchers to both confirm and refine theories related to dark matter, galaxy formation, chemical evolution, and cosmic expansion. The insights gleaned from examining our own galaxy ultimately contribute to a deeper understanding of the universe as a whole. Studying the Milky Way galaxy provides essential insights into the distribution of matter throughout the universe, as it serves as a representative model for the complex interplay of visible and dark matter in galactic systems. By examining the components of our galaxy, including stars, gas, dust, and dark matter, astronomers can develop a more comprehensive understanding of the structure and dynamics of the cosmos. One primary way the Milky Way informs us about matter distribution is through its rotation curves. Observations of how stars and gas move within the galaxy reveal that their velocities do not decrease as expected with increasing distance from the galactic center. Instead, they remain relatively constant, indicating the presence of a substantial amount of unseen mass, or dark matter, at large distances from the center. By analyzing the rotation curves, scientists can infer the distribution of dark matter in the galaxy, establishing models that describe how matter is arranged, both in our galaxy and in others. Furthermore, the study of the Milky Way's gravitational lensing effects enhances our knowledge of mass distribution. Gravitational lensing occurs when light from distant objects is bent by the gravitational field of nearby mass, allowing researchers to map the distribution of dark matter based on how much light is distorted. By observing how different regions of the Milky Way lens light, astronomers can assess both the visible and dark mass influencing these cosmic rays, offering a direct measurement of matter distribution. The Milky Way also reveals information about the intergalactic medium, which contains diffuse gas that fills the spaces between galaxies. Observations of how the Milky Way interacts with surrounding gas clouds and its neighboring satellites can illuminate the processes that govern the inflow and outflow of material. These interactions impact not only star formation within our galaxy, but also the exchange of matter between galaxies and the intergalactic medium, shaping the overall distribution of matter in the universe. Moreover, studies of the Milky Way's stellar populations and their chemical compositions inform our understanding of how matter has been distributed and recycled over cosmic time. The analysis of star formation rates and the abundance of specific elements provide a timeline of chemical enrichment, revealing how earlier generations of stars contributed to the material we observe today. This historical perspective is essential for understanding the life cycle of matter in the universe and how it has evolved across different galactic environments. Additionally, our galaxy's positioning in the cosmic web, a network of filaments and voids formed by dark matter, helps illustrate the larger-scale organization of matter in the universe. By observing the Milky Way's interactions with its neighbors in the local group and the larger Laniakea supercluster, researchers can study how gravitational forces shape the distribution of galaxies, contributing to the understanding of how structures form and evolve in the universe. Studying the Milky Way provides crucial insights into the distribution of matter in the universe by revealing the dynamics of visible and dark matter, the interactions with the intergalactic medium, and the historical processes that shape matter's evolution. The knowledge gained from our galaxy enriches our understanding of the broader cosmic environment, enabling researchers to develop more accurate models of how matter is distributed and organized throughout the universe. The Milky Way's satellite galaxies offer crucial insights into the processes of structure formation in the universe. As these smaller galaxies orbit the Milky Way, they serve as laboratories for studying the dynamics and interactions that help shape galactic structures. Their properties, behaviors, and the patterns of their distributions provide valuable information on how galaxies form and evolve over cosmic time. One significant aspect of the Milky Way's satellite galaxies is how they illustrate the effects of gravity and dark matter on structure formation. Many of these satellites are composed primarily of dark matter, and their interactions with the Milky Way can shed light on how dark matter influences galaxy dynamics. For instance, observations of the orbits and velocities of these satellites can help researchers measure the gravitational potential exerted by the Milky Way's dark matter halo. Analyzing how these dwarfs respond to gravitational forces allows scientists to refine models of dark matter distribution in both the Milky Way and in other galaxies. Additionally, the composition of the Milky Way's satellite galaxies reveals essential information about their formation and evolution. Many of these satellites are old, metal-poor galaxies, indicating that they formed early in the universe's history. Studying their stellar populations and chemical compositions helps researchers understand the processes that led to the formation of smaller galaxies and the role of environment and interactions in their evolution. For example, examining how different stellar populations are distributed within satellite galaxies can inform theories regarding star formation rates and the influences of feedback processes from supernovae or cosmic rays. The interactions between the Milky Way and its satellite galaxies can also be studied to learn about tidal forces and their implications for structure formation. The gravitational pull of the Milky Way can cause tidal stripping, where smaller satellite galaxies lose their gas and stars, gradually dissolving into the Milky Way's halo. Observing these processes helps scientists understand how larger galaxies grow through the accretion of smaller ones, and how satellite galaxies contribute to the overall mass and structure of their larger neighbors. Moreover, the distribution and variety of satellite galaxies around the Milky Way provide insights into the statistical properties of galaxy formation in the hierarchical structure formation model. The number, sizes, and types of satellites can inform researchers about the history of galaxy mergers and how the Milky Way developed over time. Comparing the Milky Way's satellite system with other galaxies, such as Andromeda, allows astronomers to probe the commonality of these processes and refine theories about the formation of galaxies in varied environments. The Milky Way's satellite galaxies are key to understanding structure formation in the universe. They provide critical data on dark matter effects, star formation processes, tidal interactions, and galaxy mergers. By studying these dwarf galaxies, astronomers can develop a more comprehensive view of how galaxies evolve, inform models of cosmic structure formation, and enhance our understanding of the universe's history and dynamics. The Milky Way's dark matter halo is a critical component of our galaxy's structure and plays a significant role in understanding the dynamics of galaxies across the universe. Dark matter halos, which are massive, invisible regions of gravitational influence surrounding galaxies, vary in size, shape, and density among different galaxies. By comparing the Milky Way's dark matter halo to those of other galaxies, astronomers can gain insights into the formation and evolution of galactic structures. One key aspect of the Milky Way's dark matter halo is its overall mass and distribution. Studies suggest that the halo's mass is approximately 1 trillion solar masses, which is significant but not unusual compared to other spiral galaxies. The density profile of the Milky Way's dark matter halo appears to follow a pattern consistent with the predictions of the standard cold dark matter model. This model indicates that dark matter density typically decreases with distance from the galaxy center, leading to a more concentrated mass in the inner regions and a more diffuse distribution outward. When comparing the Milky Way's halo to those of other galaxies, such as the Andromeda galaxy, astronomers observe notable similarities and differences. Andromeda also possesses a substantial dark matter halo, similar in mass to the Milky Way's, and the two galaxies are expected to merge in the distant future. This gives astrophysicists an opportunity to study how dark matter dynamics change in response to gravitational interactions and natures of merger events. Additionally, the characteristics of dark matter halos in dwarf galaxies provide important contrasts to those found in larger galaxies like the Milky Way. Dwarf galaxies often exhibit lower surface brightness and can have significantly different dark matter density profiles. Some of these halos are less massive and can be more irregular in shape, reflecting their different formation histories. Observing the halos of various dwarf galaxies helps scientists understand the role of environment and interaction in shaping dark matter properties, as well as how these smaller systems contribute to the overall gravitational field of larger galaxies. Furthermore, using gravitational lensing, astronomers can map dark matter distributions in a variety of galaxies, including those that are much further away than the Milky Way. These observations have revealed a diverse range of halo shapes and masses, with some galaxies exhibiting elongated or irregular dark matter distributions rather than the more spherical profiles typically expected. This diversity enhances our understanding of how different galaxy formation processes may lead to varying dark matter halo properties. By comparing the Milky Way's dark matter halo with those of other galaxies, researchers can refine existing cosmological models and better understand how dark matter influences galaxy formation and evolution. These comparisons provide critical context for interpreting the observed behaviors of galaxies and contribute to our understanding of the large-scale structure of the universe, enhancing our overall picture of how dark matter galaxies and cosmic evolution are interrelated. Studying the Milky Way provides a treasure trove of insights into galaxy evolution, as it serves as a nearby and relatively well-understood example of a spiral galaxy. By examining its structure, dynamics, and history, astronomers can gather key information about the processes that govern the formation and development of galaxies across the universe. One of the primary insights relates to the role of star formation in galaxy evolution. The Milky Way exhibits varied rates of star formation across its different regions, including the galactic disk, bulge, and halo. By analyzing the distribution of young and old stars, as well as examining the gas and dust that serve as the fuel for star formation, researchers can learn about the conditions that promote or inhibit star formation. Observations of stellar populations help to establish how these processes have changed over time, indicating how external factors, such as interactions with neighboring galaxies or variations in gas inflow, affect star formation rates. The Milky Way's interactions with its satellite galaxies also offer insights into the dynamics of galaxy evolution. Over time, our galaxy has absorbed smaller satellites through gravitational interactions, a process known as accretion. Studying how the Milky Way interacts with and merges with these smaller systems provides critical information about how galaxies grow in mass and alter their structures. The remnants of these interactions can reveal important details about the history of the Milky Way, including its past mergers and contributions to the galaxy's stellar and dark matter content. Additionally, the chemical composition of the Milky Way's stars helps us trace the history of nucleosynthesis and the recycling of material throughout the galaxy. Each generation of stars contributes to the chemical enrichment of the interstellar medium when they explode as supernova or shed their outer layers. By studying the abundance of different elements in varying stellar populations, astronomers can reconstruct the timeline of element formation and their distribution across different regions of the galaxy. This understanding is essential for modeling how elements produced in stars lead to the development of planets and the conditions that might support life. The Milky Way also highlights the role of dark matter in galaxy evolution. It is surrounded by a massive dark matter halo that influences the motion of stars and gas within it. By investigating the gravitational effects of the Milky Way's dark matter, researchers can infer properties of dark matter and its distribution, contributing to models that describe how dark matter interacts with baryonic matter. Understanding these interactions provides important clues about how galaxies have formed under the influence of dark matter over cosmic time. Lastly, the position of the Milky Way within the larger cosmic environment, such as its membership in the local group and the Laniakea supercluster, is crucial for understanding the effects of galaxy clustering on evolution. The relationships between the Milky Way and its neighbors can illustrate how galaxies change in response to their environments, revealing the effects of gravitational interactions, merger events, and the cosmic web on their formation and development. Studying the Milky Way yields important insights into galaxy evolution, encompassing star formation processes, interactions with satellite galaxies, chemical enrichment histories, the role of dark matter, and the influence of environmental factors. As astronomers continue to gather data and refine their models, These findings will contribute to our understanding of how galaxies like the Milky Way have shaped and continue to shape the universe. The star formation history of the Milky Way galaxy is intricately linked to cosmic star formation rates, providing valuable insights into how galaxies across the universe have evolved over time. By examining the star formation rates within our galaxy and comparing them to cosmic trends, astronomers can piece together a broader narrative of galaxy evolution and the processes that drive star formation on larger cosmic scales. The Milky Way has experienced varied rates of star formation throughout its history, influenced by factors such as gas availability, environmental conditions, and interactions with other galaxies. Studies of the Milky Way's stellar populations indicate that major periods of star formation occurred in significant bursts. For example, a vigorous phase of star formation is thought to have taken place during the galaxy's early development, roughly between 5 to 11 billion years ago, when the rate of star formation was considerably higher than it is today. This historical perspective helps scientists correlate the Milky Way's star formation rate with the cosmic star formation rate observed across the universe. Over time, cosmological surveys have shown that the overall rate of star formation in the universe peaked around 10 to 12 billion years ago during a period known as cosmic noon. This era marked a time when many galaxies, including those similar to the Milky Way, formed a significant fraction of their stars. By comparing the Milky Way's star formation history with these cosmic trends, researchers can better understand how the processes driving star formation in our galaxy reflect larger patterns observed in other galaxies. For instance, models that describe the decline in star formation rates in the cosmos over the last several billion years align with evidence observed in the Milky Way, which has also seen a gradual decrease in its star formation activity. The relationships between local and cosmic star formation rates also highlight the influence of environmental factors and galaxy interactions. As smaller galaxies merge with the Milky Way, they can trigger bursts of star formation due to the influx of gas and the gravitational interactions involved. Understanding these hierarchical processes helps to link the Milky Way's individual star formation history to the broader mechanisms shaping cosmic star formation rates. Additionally, studying the Milky Way allows for refined models of star formation feedback mechanisms, such as supernova explosions and stellar winds. These feedback processes can regulate the star formation rates in galaxies by removing gas from star-forming regions or enriching the surrounding medium with heavy elements. These processes are essential for understanding both the star formation history of our galaxy and the overall trends observed across the cosmic landscape. The star formation history of the Milky Way provides crucial context for understanding cosmic star formation rates, by revealing how local processes correlate with broader trends in galaxy evolution. By investigating the interplay between the Milky Way's history and universal star formation trends, astronomers can discern patterns that enhance our understanding of the fundamental mechanisms driving the birth and evolution of stars in the cosmos. The Milky Way stands out among the billions of galaxies in the observable universe due to a variety of unique characteristics that contribute to its distinct identity. While many features are shared with other galaxies, several aspects of the Milky Way provide a special perspective on galaxy formation, evolution, and the conditions that support life. One of the most notable features of the Milky Way is its position as a barred spiral galaxy. This structural form includes a central bar-shaped region made up of stars, spiral arms extending outwards, and a surrounding halo of stars and dark matter. The combination of the bar and the spiral structure contributes to the galaxy's dynamics and influences star formation processes. This specific morphology allows researchers to study how such structures form and evolve, serving as a representative example for understanding similar galaxies across the universe. The Milky Way is also uniquely situated in a relatively local and well-studied environment. As the home galaxy to our solar system, it provides astronomers with a nearby laboratory in which they can observe galactic processes in detail. The availability of a wide array of astronomical data from various wavelengths allows for comprehensive studies of its components, such as stars, gas, dust, and dark matter. This proximity enables scientists to gather high-resolution data that would be challenging to obtain from more distant galaxies. The composition of the Milky Way's stars, gas, and dust is another aspect that makes it distinctive. The galaxy exhibits a broad range of stellar populations, from ancient stars in the halo to younger stars forming in active regions within the spiral arms. Its chemical composition, reflecting a rich history of nucleosynthesis, provides insights into the evolution of matter in the universe and the processes that lead to the formation of life-friendly environments. These neighborhoods of star formation and the associated heavy element distribution enrich the study of planet formation and the potential for life elsewhere in the galaxy. Moreover, the Milky Way's interactions with satellite galaxies, such as the Large and Small Magellanic Clouds, mark it as a prime example of galactic evolution through mergers and accretion. The ongoing gravitational interactions and the effects of tidal forces have significant implications for gaining insights into the mechanisms of galaxy growth, as well as for understanding how these processes shape stellar populations and dynamics over time. Another notable aspect is the presence of a supermassive black hole known as Sagittarius A star at the center of the Milky Way. The study of this black hole and its influence on the surrounding stellar environment helps to illuminate the relationship between central black holes and the properties of their host galaxies. Research conducted around Sagittarius A star enhances understanding of the role that black holes may play in galaxy formation and evolution. Finally, the Milky Way's role in the search for extraterrestrial life makes it particularly unique. Its abundant star systems, including a variety of potentially habitable planets discovered through exoplanet studies, offer the potential for life beyond Earth. Understanding the conditions in the Milky Way that favor the emergence of life is an exciting frontier in astrobiology. The Milky Way's unique characteristics, its barred spiral structure, proximity for detailed study, diverse stellar populations, interactions with satellite galaxies, central supermassive black hole, and potential for hosting extraterrestrial life, distinguish it among the multitude of galaxies in the observable universe. These features provide crucial insights into galactic processes and enhance our understanding of the larger framework of cosmology and the evolution of the universe.